Hello, and welcome to another science lecture to help you rest. Tonight, we will talk about the geysers and hot springs of Yellowstone National Park. We will explore the deep heat, the journey of water, and the intricate plumbing that creates these natural wonders. There is no need to focus too intently. The information is here to provide a calm background for your mind to settle. If you would like, you can subscribe to the channel for more lectures like this one, or leave a comment below. Your interaction is appreciated but not required. Before we begin, I have a simple question for you. When you think of Yellowstone, what is the very first image or feature that comes into your mind? Is it a geyser, a hot spring, an animal, or something else entirely? There is no right or wrong answer. Please feel free to write your simple 1 or 2 word answer in the comment section below. Now, find a comfortable position. Lie back, turn the screen off if you wish, and just listen to the sound of my voice. Close your eyes and let the day's thoughts begin to fade. We are not in a hurry. We will simply talk about rocks and heat and water. We will begin our journey far beneath the surface of the earth, in a place of immense pressure and unimaginable temperature. We will begin with the great engine that powers all of Yellowstone. Part 1. The Great Heat Engine. Under the earth. To understand anything that happens on the surface in Yellowstone National Park, we must first travel deep into the ground. We must go down past the soil, past the rock layers you might see in a road cutting, past the foundations of any buildings, and continue downwards for many miles. The geysers, the hot springs, the bubbling mud, all of these surface expressions are merely the final, visible signs of a much larger and much more powerful system that operates in total darkness, under immense pressure, deep within the crust of our planet. This system is a heat engine. It is a source of profound and ancient thermal energy that makes Yellowstone one of the most geologically active places on the entire surface of the Earth. The ultimate source of this heat is a feature known as a geological hotspot. A hotspot is not a fire in the traditional sense. There is no wood burning, no fuel being consumed in a way we would recognize. Instead, a hotspot is a place where a column of exceptionally hot rock rises from deep within the Earth's mantle. Imagine the Earth as a large piece of fruit, like a peach. The thin skin is the crust, the part we live on. Beneath the skin is the thick, fleshy part, which is the mantle. The mantle is not liquid rock in the way we often imagine it. For the most part, it is solid rock, but it is so hot and under such great pressure that it can flow very, very slowly, like incredibly thick tar or warm wax. This movement happens over immense timescales, over millions of years. Deep within this mantle, perhaps starting at the boundary with the Earth's even hotter core, a plume of material that is hotter and less dense than the surrounding rock begins to rise. This is the hotspot plume. This plume of hot mantle rock pushes its way upwards, slowly and relentlessly, like a bubble rising through a very thick liquid. As it gets closer to the surface, the pressure on it decreases. This decrease in pressure allows some of the rock in the plume to begin to melt, forming what we call magma. This magma is the liquid rock that is the direct source of the heat for Yellowstone. The Yellowstone hotspot is a stationary feature. It has been in roughly the same place for a very long time, for at least 17 million years. The plume itself stays put, anchored deep within the Earth's mantle. However, The surface of the Earth is not stationary. The Earth's crust, the thin skin of our peach, is broken into many large pieces called tectonic plates. These plates are constantly moving, drifting across the surface of the planet at a speed of a few centimeters per year, about the same speed that your fingernails grow. The place we know as Yellowstone is located on the North American plate. This massive slab of crust is slowly but surely drifting in a southwesterly direction. Imagine placing a piece of paper over a lit candle. The candle flame is the hotspot, fixed in place. The paper is the North American plate, slowly sliding over the top of the flame. As the paper moves, the candle will scorch a line across it. This is precisely what the Yellowstone hotspot has done to the North American plate. It has left a scar, a track of its immense heat across the landscape. This track is visible today as a feature called the Snake River Plain, a long, arc-shaped depression in the land that stretches for hundreds of miles across the state of Idaho, leading directly to Yellowstone. Each major point along this track marks the location of a former massive volcanic caldera, a collapsed volcano crater. As the plate moved over the hotspot, the heat from the plume would build up beneath the crust. This heat would melt the rock of the crust, creating a huge underground chamber of magma. Eventually, the pressure in this chamber would become too great, leading to a cataclysmic supervolcanic eruption. These were not eruptions like the ones we see from a typical cone-shaped volcano. These were events on a scale that is difficult to comprehend. They released thousands of times more material than any volcanic eruption in recorded human history. After such a massive eruption, the ground above the now emptied magma chamber would collapse downwards, creating a vast depression, a caldera. The North American plate continued its slow, inexorable drift to the southwest. The hot spot, remaining in place, would then begin the process again, heating the new section of crust that had moved over it. Over millions of years, this process repeated itself, leaving a chain of ancient calderas across Idaho. The oldest caldera from this hotspot is near the border of Oregon and Nevada, from around 16 or 17 million years ago. As you travel northeast along the Snake River Plain, the calderas become progressively younger. The hotspot appears to have moved, but it is the plate that is in motion. Yellowstone National Park sits directly on top of the hotspot right now. It is the current active center of this massive geological system. The immense Yellowstone caldera that dominates the park's geography is the result of the most recent super eruption, which occurred about 640,000 years ago. So, when we talk about the heat engine under Yellowstone, we are talking about this direct connection to the Earth's deep mantle. It is a conduit of primal heat that has been shaping this corner of the world for many millions of years. This heat is what we must understand first and foremost. Without this heat, there would be no geysers, no hot springs, nothing of the sort. The park would be just another section of the Rocky Mountains. The heat is the primary ingredient. Let us now focus on the structure that holds this heat just beneath the park's surface. This structure is the magma chamber. It is not a cavern of sloshing liquid rock, as is often depicted. It is a much more complex system. In reality, there are two magma chambers stacked on top of each other. The deeper chamber is larger and contains a type of magma called basaltic magma. This magma comes more directly from the mantle plume itself. It is extremely hot and is more fluid than other types of magma. This deeper chamber sits between 20 and 50 kilometers beneath the surface. It is a vast reservoir of heat and molten rock. Above this deep chamber, there is a second, shallower magma chamber. This one is located only about 5 to 16 kilometers beneath the ground. This is incredibly shallow in geological terms. This upper chamber is filled with a different kind of magma, a rhyolitic magma. This magma is formed when the heat from the lower basaltic chamber melts the rock of the Earth's crust itself. This rhyolitic magma is less hot than the basalt, and it is much thicker and stickier, more like a thick paste or a slushy. It is not a completely liquid body. Instead, scientists believe it is a sponge-like body of hot rock, a crystal mush. It is a mixture of solid crystals, molten rock, and dissolved gases like water vapor and carbon dioxide. This upper magma chamber is enormous. It is estimated to be about 90 kilometers long and about 50 kilometers wide. It is a vast subterranean reservoir of heat, a blistering hot pancake of semi-molten rock that lies just a few miles beneath the feet of anyone walking through the park. The amount of heat contained within this magma chamber is almost beyond calculation. The temperatures here are well over 800 degrees Celsius. This heat radiates upwards, constantly and powerfully, through the solid rock that lies above it. It is like having a gigantic furnace operating just below the ground. This layer of rock between the top of the magma chamber and the surface of the Earth is what we call the caprock. This caprock is fractured and cracked, full of faults and fissures created by the immense pressure from below and by past earthquake activity. It is this network of cracks that allows the story of Yellowstone to continue, as we will see later. But for now, the important concept is the heat source. Let us think again about the scale of this heat engine. The hotspot plume originates hundreds, perhaps thousands of kilometers down in the mantle. It is a feature that connects the surface world directly to the deep interior of the planet. This plume has been consistently delivering heat to the same spot for a duration of time that is difficult for a human mind to grasp. 17 million years is a vast expanse of time. During this time, entire species have evolved and gone extinct. Mountain ranges have risen and eroded away. The very continents have shifted their positions. Yet, the hotspot has remained a persistent and powerful source of thermal energy. The movement of the North American plate over this hotspot is the second critical component of this engine. This movement, at a rate of about 4 to 5 centimeters per year, is what created the long trail of volcanic activity. It is a geological conveyor belt. As one section of the plate is cooked by the hotspot and erupts, it then moves on, and a new section of crust is positioned over the heat source. The current location of Yellowstone is simply the now point on this long timeline. The park is not just a place of scenic beauty. It is the active, breathing, and sometimes violent expression of an ongoing geological process that has been unfolding for eons. The magma chamber itself, this two-tiered system, acts as the immediate heat source for all the surface features. Let us describe it again in simple terms. Far below, there is a deep source of very hot, fluid, melted rock. This rock comes from the mantle plume. Above it, and much closer to us on the surface, is a larger, cooler, stickier reservoir of melted rock. This shallower reservoir gets its heat from the one below it. This upper chamber is like a giant hot plate buried just under the ground. It is this hot plate that cooks everything above it. It is what heats the rock, and crucially, it is what heats any water that finds its way down from the surface. The sheer volume of this magma chamber is staggering. If you could somehow remove all the magma from the upper chamber, it would be enough to fill the Grand Canyon more than 11 times over. It is not a small, localized pocket of heat. It is a feature on a continental scale. The ground in Yellowstone is constantly being pushed up and warped by the pressure of this magma beneath it. Scientists, using sensitive instruments, can measure the ground rising and falling by several centimeters per year as the magma chamber inflates and deflates like a slowly breathing giant. The rock that makes up the land in Yellowstone is also a product of this heat engine. The park is dominated by rhyolite, a type of volcanic rock that forms when rhyolitic magma cools. The vast plateaus of the park are made of thick layers of this rock deposited during past massive eruptions. This rock is rich in a mineral called silica, which is the same basic component of sand and glass. This silica plays a very important role in the formation of geysers, a detail we will explore later. But the rock itself is a testament to the nature of the heat engine. It is the cooled and solidified result of the very process that is still active today, deep underground. So, to summarize this first part, the foundation of everything in Yellowstone is heat. This is not normal background heat from the Earth. It is a concentrated and powerful flow of thermal energy from a geological hotspot. This hotspot is a stationary plume of hot rock rising from the deep mantle. The North American tectonic plate is sliding over this hotspot, and Yellowstone is its current location. This heat has created a massive, two-level magma chamber just a few miles beneath the surface. This chamber, particularly the vast, shallower upper chamber, acts like a giant burner on a stove, constantly heating the ground above it. This process is relentless. It does not stop for night or day, for winter or summer. The flow of heat is constant, a powerful and invisible force that defines the entire region. It is this underground furnace that makes Yellowstone unique. Every other part of the story, every geyser, every colorful pool, every bubbling pot of mud, is a direct consequence of this great heat engine. They are all just different ways that this immense, deep heat finds a way to express itself on the cool surface of the Earth. Understanding this foundation is critical. Before we can talk about water or plumbing, we must first and foremost appreciate the source of the energy. We must picture that vast, dark, and incredibly hot world that exists just a short distance beneath the pine forests and rivers of the park. It is a world of pressure, of melted rock, and of a heat so intense it can power the spectacular displays we see above. The entire park is like the thin lid on a pot of boiling water, and the heat engine is the flame underneath. Let us revisit the components of this engine one more time to ensure the picture is clear. First, there is the source of the plume deep in the mantle. We cannot see it, we cannot directly measure it, but we can see its effects. This is the ultimate engine, the prime mover of the entire system. It is a column of rock that is hotter and more buoyant than its surroundings, and so it rises. It has been rising for a very long time. Second, there is the interaction with the tectonic plate. The plate is the rigid crust of the Earth, moving slowly but with unstoppable force. The hotspot acts like a cutting torch, scarring the bottom of the plate as it passes over. This movement is what spreads the volcanic activity out over a long line, creating the Snake River Plain and positioning the active volcanic center in its present location in Wyoming, Montana, and Idaho, the three states that Yellowstone National Park occupies. Third, there is the result of this interaction, the magma chamber. This is the more immediate part of the heat engine. It is the holding tank for the molten rock generated by the hotspot. The dual structure, with a deep basaltic chamber and a shallower rhyolitic chamber, is a key feature. The lower chamber is the direct result of the melting mantle plume. The upper chamber is the result of the lower chamber melting the continental crust above it. This upper chamber is the one that directly influences the surface geology and the hydrothermal systems. Its enormous size and relative shallowness mean that its influence is spread over a very wide area. The Yellowstone caldera, the giant collapsed crater from the last super eruption, roughly outlines the location of this shallow magma chamber. The caldera itself is about 72 kilometers long and 55 kilometers wide. When you are standing in the middle of Yellowstone, for instance near the Old Faithful Geyser, you are standing directly inside this massive volcanic crater on top of this immense reservoir of heat. The heat does not just radiate upwards. The pressure from the magma and the associated gases also pushes upwards. This creates stresses in the crustal rock above. These stresses lead to faults, which are fractures in the rock where movement has occurred. It also creates joints, which are smaller cracks and fissures. This fracturing of the rock is essential. Without a cracked and permeable crust, the heat would be largely trapped below. It would build up over hundreds of thousands of years until the next super eruption. But the cracks and faults provide pathways. They act as conduits. They allow the heat to escape in a more controlled, continuous manner. And more importantly, they allow something from the surface to travel down towards the heat. That something is water. The entire system, from the mantle plume to the magma chamber to the fractured rock above, is a cohesive whole. Each part is necessary for the final result. The hotspot provides the raw energy. The moving plate positions the action. The magma chamber stores and transfers the heat closer to the surface. And the fractured rock provides the plumbing. We have now established the furnace. It is a geological engine of immense scale and power, operating constantly just below the surface. Its presence is the single most important fact about Yellowstone. Every strange and wonderful thing in the park owes its existence to this hidden world of heat and pressure. The silence of the deep earth is the source of the roar of the geysers. The darkness of the magma chamber is the source of the brilliant colors in the hot springs. This is the first half of the equation. The heat is present, it is powerful, and it is waiting. The next part of the story involves what happens when water from the sky meets this incredible heat from the deep earth. But that is a story for the next part. For now, it is enough to picture this engine, to imagine its scale, and to understand that it is the foundation upon which everything else is built. The land of Yellowstone is not solid, stable ground. It is the thin, fragile ceiling of an active volcano. It is a landscape powered by a direct line to the planet's molten interior. And that is why it is unlike almost any other place on Earth. It is a window into the powerful forces that shape our world, a place where the heat of the Earth's heart is made visible. Part 2. The Journey of Water. In our last discussion, we established the first and most crucial ingredient for the wonders of Yellowstone. We spoke of the great heat engine, the geological hotspot deep in the Earth's mantle, and the enormous, shallow magma chamber that sits just a few miles beneath the park. This chamber is the furnace, a relentless and powerful source of thermal energy. But a furnace alone does not create a geyser. Heat by itself is just heat. To create the hydrothermal features we see on the surface, a second ingredient is required. This ingredient is common, familiar, and essential for all life as we know it. This ingredient is water. The story of Yellowstone's geysers and hot springs is the story of what happens when these two fundamental forces of nature, immense heat and vast quantities of water, meet each other deep within the crust of the earth. This part of our lecture will be dedicated entirely to the journey of that water. It is a long journey, a slow journey, one that can take centuries or even thousands of years to complete. We will follow the water from the moment it falls from the sky as rain or snow down through the soil, deep into the fractured rock of the Yellowstone Plateau, until it finally reaches the zone of intense heat radiating from the magma chamber below. Our journey begins high in the atmosphere above the Rocky Mountains. Yellowstone is a high-altitude place. Much of the park is a broad volcanic plateau with an average elevation of about 8,000 feet above sea level. This high elevation has a profound effect on the weather. As moist air from the Pacific Ocean travels eastward across the continent, it is forced to rise up over the mountain ranges. As the air rises, it cools. Cooler air cannot hold as much moisture as warmer air, so the water vapor within it begins to condense, forming clouds. These clouds gather over the mountains and plateaus of the park, becoming thick and heavy with water. This process leads to a great deal of precipitation, far more than the surrounding lowlands receive. In Yellowstone, this precipitation falls primarily in two forms: rain in the short summer months, and snow for the long duration of autumn, winter, and spring. Let us first consider the snow. Winter in Yellowstone is long and severe. Snow begins to fall in October or November and continues, often relentlessly, through April or even May. It is not a light dusting of snow. It is a deep and heavy accumulation. Storm system after storm system rolls across the high country, each one depositing a fresh layer of white powder. The individual snowflakes are intricate crystals of ice, formed high in the cold atmosphere. Each one is unique, a small, six-sided structure, but as they fall by the trillions upon trillions, they lose their individual identity and become part of a collective, a vast white blanket that drapes itself over the entire landscape. The snow covers the pine forests, fills the open meadows, and buries the dormant geothermal features under a thick layer of insulation. The weight of this snowpack is immense. As new layers fall on top of old ones, the snow at the bottom becomes compressed. The delicate, airy crystals are crushed together, squeezing out the air between them and turning into a denser, more granular form of ice. This snowpack can become many feet deep, sometimes 10, 15, or even 20 feet deep in the higher elevations. For more than half the year, this is where the water of Yellowstone is stored. It is locked away in a solid, frozen state, a massive reservoir of future water waiting for a change in season. This deep snowpack acts as a protective layer, insulating the ground from the frigid winter air. It also represents a slow release mechanism for the water. If all this precipitation fell as rain, it would run off the surface very quickly, flooding the rivers and disappearing from the area in a short amount of time. The snow, however, holds the water in place for months, ensuring a steady supply for the systems below. Then, as the days grow longer and the sun climbs higher in the sky in late spring and early summer, the great melt begins. The process is slow at first. The surface of the snow begins to glisten with a thin film of moisture during the warmest part of the day. Small trickles of water begin to form, seeping down into the snowpack below. As the temperatures rise more consistently, the melt accelerates. The once pristine white snowpack becomes heavy and saturated with liquid water. Streams and rivulets appear on its surface, carving small channels. The entire landscape begins to weep water. The sound of dripping and running water fills the air, a constant reminder that the vast frozen reservoir is being released. This meltwater is the primary source of water for the entire geothermal system of the park. It is pure water, distilled by the atmosphere, and now it is beginning its long journey downwards. The rain that falls during the summer contributes as well. The summer thunderstorms can be intense, dropping a large amount of water in a short period. This rainwater, along with the continuous meltwater from any remaining snowfields at the highest elevations, soaks into the ground, joining the water from the great spring melt. So, we have our source. Hundreds of inches of precipitation fall on the Yellowstone Plateau each year, providing a massive and consistent supply of water. This water is the lifeblood of the geysers and hot springs. Without this constant replenishment from the sky, the geothermal system would eventually run dry. Now, the water has arrived on the surface. A single drop of meltwater, let us say, has just been released from the edge of a melting snowbank. Its journey into the earth is about to begin. The first stage of this journey is called infiltration. This is the process of water soaking into the ground. The surface of Yellowstone is not a solid, impermeable sheet of rock. It is covered by a layer of soil, a mixture of weathered rock particles, organic material from decaying plants, and a myriad of tiny living organisms. This soil is porous. It is full of tiny spaces and gaps between the individual particles. When the water drop lands on the soil, it is pulled downwards by two forces, gravity and capillary action. Gravity is the simple downward pull of the earth. Capillary action is the ability of water to be drawn into small spaces, the same force that pulls water up into a paper towel. The water drop joins with other drops seeping into the topsoil. It navigates a microscopic maze of soil, particles and plant roots, the roots of the grasses, wildflowers and pine trees that cover the park create channels and pathways that help the water penetrate deeper into the ground. The water moves past earthworms and burrowing insects, through layers of decaying pine needles and rich humus. This upper layer of soil acts as a filter, removing any dust or impurities the water may have picked up from the atmosphere. The journey through this first few feet of soil is relatively quick, a matter of hours or days. The water continues to be pulled downwards by gravity, leaving the zone of plant roots and entering the subsoil and the layers of weathered rock fragments that lie beneath it. Below the soil, the water encounters the rock of the Yellowstone Plateau itself. This rock, as we learned in the first part, is primarily volcanic. It is rhyolite and volcanic tuff, rocks that were formed from the ash and lava of past super eruptions. This rock is not a solid, unbroken mass. It is full of pores, cracks, and fissures. Some of this rock is very porous, like a hard sponge, allowing water to soak directly into it. But more importantly, the entire plateau is a fractured landscape. The immense geological forces at work here, the upward pressure from the magma chamber, and the constant shaking from small earthquakes have created a vast and complex network of cracks that extend deep into the earth. These cracks are the highways for the groundwater. Our drop of water, having made it through the soil, now finds one of these tiny fissures in the rock. It joins a slow but steady trickle of other water drops, and its true descent begins. The journey now becomes much, much slower. The movement of water deep underground is not like a river flowing on the surface. It is a creeping, seeping, percolating process that can be incredibly slow. The water may move only a few feet in an entire year. It is a journey that takes place in complete darkness, under the steadily increasing weight of the rock above. The pathways are not straight. They are a chaotic, three-dimensional labyrinth of interconnected fractures. The water is forced to wind its way downwards, following the path of least resistance, ever deeper into the crust. As the water descends, the world around it changes dramatically. On the surface, there is life, air, and sunlight. Just a few hundred feet down, all of that is gone. There is only rock, water, and darkness. The pressure begins to build. At the surface, the water is under 1 atmosphere of pressure. For every 10 meters, or about 33 feet, that it descends, the pressure increases by another atmosphere. As our water drop travels thousands of feet down, the pressure becomes immense. It is being crushed by the weight of the entire column of rock and water that lies above it. This incredible pressure is one of the key factors that allows the magic of Yellowstone to happen. Simultaneously, as the water goes deeper, it begins to get warmer. The Earth has a natural temperature gradient. The deeper you go, the warmer it gets. This is true everywhere on the planet. But in Yellowstone, this gradient is extreme. Because the magma chamber is so close to the surface, the rock is exceptionally hot at relatively shallow depths. The water, which started its journey at a temperature just above freezing, now finds itself percolating through rock that is getting progressively hotter. At a depth of a few thousand feet, the water temperature might reach 50 or 60 degrees Celsius. As it continues its descent, it gets hotter and hotter. 100 degrees Celsius, the normal boiling point of water at sea level, is reached and then surpassed. 200 degrees Celsius, 250 degrees Celsius. The water is now incredibly hot, far hotter than boiling water on the surface. This leads to a very important question. If the water is heated to temperatures well above 100 degrees Celsius, why does it not flash into steam and explode? The answer is the immense pressure we mentioned earlier. The boiling point of water is not a fixed number. It depends entirely on the pressure surrounding it. At sea level, with 1 atmosphere of pressure, water boils at 100 degrees Celsius. If you go to the top of a high mountain, the air pressure is lower, and water will boil at a lower temperature, perhaps 90 degrees Celsius. This is why it takes longer to cook things in boiling water at high altitudes. Conversely, if you increase the pressure, you increase the boiling point. This is the principle behind a pressure cooker. By sealing the pot, you increase the pressure inside, which allows the water to reach a temperature of 120 degrees Celsius or more without boiling, cooking the food much faster. Deep beneath Yellowstone, the water is in a natural pressure cooker of planetary scale. The weight of the thousands of feet of rock and water above it creates such enormous pressure that the boiling point of the water is raised to a very high temperature. The water can be heated to 200, 300, or even more than 400 degrees Celsius and still remain in a liquid state. This is a critical concept to understand. The water deep in Yellowstone's geothermal system is not boiling. It is a liquid, but it is a liquid that is holding a tremendous amount of thermal energy. Scientists call this state superheated water. Our drop of water has now completed this part of its journey. It may have taken 500 years, or 1,000 years, or even longer. It has traveled perhaps 3 miles straight down into the Earth's crust. It is now part of a vast, unseen reservoir of superheated liquid. This is not an open cavern of water. It is simply the same fractured rock. But now, all the cracks and pores are completely saturated with this incredibly hot, highly pressurized water. This water is also no longer pure, as it has passed through the rock for centuries. This very hot water has acted as a powerful solvent. It has dissolved minerals out of the surrounding rock. One of the most important minerals it dissolves is silica, the main component of the rhyolite rock. This dissolved silica will play a very important role when the water eventually returns to the surface. The water also picks up dissolved gases from the deep earth, gases like carbon dioxide, hydrogen sulfide, and others that are released by the cooling magma far below. So let us pause and create a clear picture of the situation deep underground. Miles below the forests and meadows, there exists a vast sponge-like network of cracked rock. This network is completely filled with water that has been heated to hundreds of degrees by the nearby magma chamber. This water is kept in a liquid state by the crushing pressure of everything above it. It is rich in dissolved minerals and gases. This deep reservoir is the heart of the hydrothermal system. It is the charged and ready battery that will power the geysers and hot springs. The journey of the water is a continuous cycle. While our drop of water has just completed its descent, other drops are beginning their journey at the surface, and still other water is beginning its journey back up towards the surface. The entire system is constantly being recharged by the rain and snow. It is estimated that the amount of water that falls on Yellowstone each year is more than enough to supply all of the rivers that flow out of it, as well as all of the water that is ejected from its thousands of geysers and hot springs. The system is in a state of dynamic equilibrium. Water comes in from above, is heated down below, and then makes its way back to the surface. Let's re-examine the slowness of this process, as it is a concept that is hard to grasp. We live our lives in minutes, hours, and days. Geological processes operate on timescales of centuries and millennia. The water that erupts from Old Faithful Geyser today did not fall as rain last week, or last year, or even last century. It fell on the Yellowstone Plateau when medieval castles were being built in Europe. It has spent that entire time on a slow, dark journey, seeping through rock mile after mile, gradually getting hotter and more pressurized until today, when it finally completes its journey in a magnificent eruption. This immense timescale gives the water time to absorb so much heat and so many minerals. It is a process of long, slow cooking. This underground plumbing system is not static. It is constantly changing. Small earthquakes, which are very common in Yellowstone, can open new fractures in the rock or close off old ones. This can reroute the underground flow of water, causing some hot springs to dry up and new ones to appear overnight. The constant deposition of minerals by the water can also clog up the plumbing over time, changing the behavior of a geyser or extinguishing it altogether. The system is alive and dynamic, even though its processes are largely hidden from our view and operate on a timescale much longer than a human life. So, to summarize this second part, the journey of water is a critical component of the Yellowstone story. It begins with immense amounts of precipitation, mostly snow, that falls on the high plateau. This water is then stored for months in the snowpack before being released during the spring melt. It infiltrates the ground, passing through the soil and into the porous and fractured volcanic rock below. It then begins a very long, very slow journey downwards, percolating through a complex labyrinth of fissures deep into the Earth's crust. As it descends, the pressure and temperature increase dramatically. The water is heated by the nearby magma chamber to temperatures far above its surface boiling point, but it is kept in a liquid state by the enormous pressure. This superheated water dissolves minerals and gases from the surrounding rock. It resides in a deep, hot reservoir, a storehouse of thermal energy, waiting for a pathway to return to the surface. This journey is the essential link between the sky and the deep earth. It is the process that transports the cool, fresh water from the surface down to the geological furnace. It transforms the water, charging it with heat and minerals, turning it into the potent fluid that creates the geothermal wonders of the park. We have now assembled the two main ingredients. We have the heat engine, the furnace, which we discussed in the first part, and now we have the medium for transferring that heat, the superheated water that has completed its long journey from the surface. The stage is now set for the next part of our story, which is what happens when this hot, pressurized water finds a fast track back to the surface. It is the structure of this return path that will determine whether the water emerges calmly as a hot spring or erupts violently as a geyser. The long, slow descent is over. The potential energy is stored. The journey back up is about to begin. Part 3. The mechanics of a geyser eruption. We have now established the two essential pillars of the Yellowstone geothermal system. First, we have the immense and unrelenting heat originating from the mantle plume and stored in the vast magma chamber that lies just a few miles beneath the surface. This is the engine. Second, we have the water, which falls as rain and snow, embarks on a journey lasting centuries, seeping miles down into the crust, where it becomes superheated and pressurized. This is the fuel and the medium. Now, we will explore what happens when this highly energized water finds a pathway back to the surface. Not just any pathway, but a very specific and special kind of pathway. A pathway that is constricted and confined. One that does not allow for the easy escape of heat and pressure. This is the pathway that creates a geyser. A geyser is, in its simplest form, a hot spring that erupts. The eruption is a temporary and violent release of a tremendous amount of stored energy. This entire part of our lecture will be dedicated to understanding the precise mechanics of that eruption. We will build a model of a geyser's plumbing system in our minds, and then walk through a single eruption cycle. step by excruciating step, from the quiet moments of refilling to the final, roaring release of steam. To begin, we must understand the structure that makes a geyser possible. This is its underground plumbing system. It is not a simple, straight pipe leading from the deep heat source to the surface. If it were, the heat would escape too easily, and an eruption would never happen. Instead, a geyser's plumbing is a complex, irregular, and often chaotic network of interconnected fissures, chambers, tubes. Imagine a series of oddly shaped rooms and crooked hallways deep within the rock, all connected to each other and leading upwards to a single, small opening at the ground. This labyrinthine structure is crucial. The rock itself, the material that forms the walls of this plumbing system, is the volcanic rhyolite we have discussed. Over thousands of years, the superheated water, rich in dissolved silica, has flowed through these passages. As the water gets closer to the surface or enters slightly cooler areas, it can no longer hold as much dissolved silica. The silica begins to precipitate out of the water, depositing a hard, glass-like mineral layer on all the surfaces it touches. This mineral deposit is called siliceous sinter, or sometimes geyserite. It is essentially a form of opal. This sinter coating is incredibly important. It acts like a sealant, a natural waterproofing and strengthening agent. It lines the inside of the geyser's plumbing, sealing up small cracks and making the walls of the system pressure tight. This allows the system to withstand the incredible pressures that build up before an eruption. Without this strong, sealed lining, the pressure would simply dissipate into the surrounding rock, and the geyser would fail to erupt. The sinter lining also helps to insulate the system, keeping the heat contained within the water. The single most important feature of a geyser's plumbing system, the feature that distinguishes it from a calm hot spring, is a constriction. Somewhere in the upper part of the system, there is a narrow point, a bottleneck. This could be a tight bend, a section where the main tube becomes very skinny, or a series of small chambers connected by tiny openings. This constriction acts like a cork in a bottle. It prevents the water in the system from circulating freely. In a normal hot spring, the plumbing is wide open. Hot water at the bottom is less dense, so it rises. As it reaches the surface, it cools, becomes denser, and sinks back down. This creates a constant, gentle circulation called convection. This circulation carries heat to the surface and releases it calmly as steam. But in a geyser, the constriction stops this from happening. The water becomes trapped below the narrow point, and the heat energy it contains cannot easily escape. It is this trapping of energy that leads to an eruption. So let us build our mental model of a typical geyser. Imagine a deep, vertical crack in the rock that serves as the main reservoir. This crack extends thousands of feet down, reaching into the zone of superheated water. Leading up from this main reservoir is a tube, also formed by natural fractures. This tube is not smooth or straight. It has side pockets, chambers, and bends. And somewhere in its upper third, there is a narrow, pinched section. This is our constriction. Above this constriction, the tube continues to the surface, where it may open into a small pool, or, more commonly, for the type of geyser we will first describe, it ends in a cone-like mound of accumulated sinter deposit with a hole in the top. This is the structure. A deep reservoir, a complex tube, a critical constriction, and a surface vent. It is a natural pressure cooker designed by geology over millennia. Now, let us begin the cycle. We will start in the moments just after a full eruption has finished. The geyser has expelled a huge volume of water and steam. Its plumbing system is now largely empty. The pressure has been released, and a relative quiet has descended upon the vent. The first phase of the new cycle is called the recharge phase. The deep reservoirs of superheated water are still present far below, but the immediate plumbing of the geyser needs to be refilled. Cooler groundwater from the surrounding rock, the same water that has been on its long journey from the surface, begins to seep back into the lower parts of the geyser system. This water is significantly cooler than the superheated water. It is replacing, but it is still quite warm, perhaps 50 or 60 degrees Celsius. It trickles and flows through the network of cracks, slowly making its way into the main conduits of the geyser. Imagine you could hear this process. It would be a sound of slow dripping, of quiet gurgling, as water finds its way into the empty chambers. The water level inside the hidden plumbing begins to rise. It fills the deepest chambers first, then slowly climbs up the main tube. This refilling process can take minutes or hours, depending on the geyser. For a geyser like Old Faithful in Yellowstone, this recharge takes up the bulk of the time in its roughly 90-minute cycle. The water rises steadily, a column of liquid slowly building inside the rock. It passes through the lower chambers, submerging them one by one. Eventually, the water level reaches the critical constriction in the upper part of the system. It flows through the narrow opening and continues to rise, filling the plumbing all the way to the surface, where a small amount of water may become visible in the vent. The geyser's plumbing system is now full of water. The recharge phase is complete. Now, the second phase begins. This is the heating phase. The column of water is now sitting in the plumbing, which is surrounded by intensely hot rock. The heat from the rock begins to conduct into the water, raising its temperature. This heating does not happen uniformly. The water at the very bottom of the system, which may be thousands of feet deep, is closest to the primary heat source. It gets hot very, very quickly. The water at the top of the column, near the cool surface of the earth, remains much cooler. A steep temperature gradient is established along the length of the water column. It is cool at the top and incredibly hot at the bottom. The constriction in the plumbing plays its critical role here. It prevents the hot water at the bottom from rising and mixing with the cool water at the top. The convection that would normally carry this heat away is choked off by the narrow passage. The water at the bottom has nowhere to go. It just sits there, absorbing more and more and more heat from the surrounding rock. As the water at the bottom of the column heats up, something fascinating happens. It reaches and then exceeds the normal boiling point of 100 degrees Celsius, but it does not boil. As we discussed in the previous part, the immense pressure from the thousands of feet of water pressing down from above raises the boiling point significantly. The water at the bottom of the system might reach a temperature of 130 degrees Celsius, or 150 degrees Celsius, or even higher, yet it remains in a liquid state. It has become superheated. This is a state of tremendous stored energy. The water molecules are vibrating with thermal energy, desperate to fly apart and turn into steam. But the crushing weight of the water column above holds them together as a liquid. The entire lower part of the geyser's plumbing system has now become a repository of high-pressure, superheated water. It is a loaded weapon, waiting for a trigger. The trigger comes in the form of the first steam bubbles. The heating process is not perfectly stable. There might be a side chamber in the plumbing, slightly higher up than the very bottom, where the pressure is a little bit lower. In this chamber, a pocket of water might be the first to reach its specific boiling point for that depth and pressure. When it does, it flashes into steam, or perhaps a sudden drop in atmospheric pressure on the surface from a passing weather system is enough to slightly lower the pressure throughout the column, triggering boiling at the hottest point. Whatever the cause, few bubbles of steam are formed in the superheated water deep within the system. This is the beginning of the end of the quiet phase. A single bubble of steam is a powerful thing. When a volume of water turns to steam, it expands to over 1,500 times its original volume. So, even a few small bubbles of steam forming in a confined space create a massive and sudden increase in volume. These first steam bubbles, being much less dense than the water around them, immediately begin to rise up the main tube of the geyser. They are buoyant, like a cork held under water and then released. As these bubbles rise, they act like a piston. They push the slug of water that is above them in the tube upwards. This initial push is often visible on the surface. For many geysers, the eruption begins not with a single great blast, but with a series of preliminary splashes. Water will surge up into the geyser's cone and spill over the side. This is the water from the very top of the column, being pushed out by the rising steam bubbles from deep below. This preliminary splashing is a sign that the eruption is imminent. Now, we arrive at the critical moment, the point of no return. The rising steam bubbles have pushed a significant amount of water out of the top of the plumbing system. This water has splashed onto the ground and drained away. The total length, and therefore the total weight, of the water column inside the geyser has been reduced. This reduction in weight causes a reduction in pressure on all the water that remains below. This is the trigger for the chain reaction. Let us think about the superheated water at the bottom. It was at, for example, 130 degrees Celsius, and the pressure was just high enough to keep it liquid. Its boiling point at that pressure was perhaps 131 degrees. It was on the very edge of boiling. But now, because the water column above it is shorter, the pressure on it suddenly drops. With this drop in pressure, its boiling point also drops. Its new boiling point might be 128 degrees Celsius, but its actual temperature is still 130 degrees. It is now 2 degrees above its boiling point. It is in an incredibly unstable state. Instantly, and with explosive force, this superheated water flashes into a massive volume of steam. This is not a gentle simmering. It is a violent, instantaneous conversion of liquid to gas. The resulting explosion of steam creates a powerful upward thrust, pushing much more water out of the plumbing system. This ejects a huge volume of water from the vent, which in turn causes an even greater reduction in the weight of the water column. This further reduces the pressure on the water that is even deeper in the system. This deeper water, which was also superheated and stable a moment ago, now finds itself above its new, lower boiling point. So it too flashes into steam, creating an even bigger explosion of volume. ejecting even more water and causing a yet greater drop in pressure on the water below it. This is the chain reaction. A drop in pressure causes boiling, which causes an eruption of water, which causes a greater drop in pressure, which causes more violent boiling, which causes a bigger eruption of water. The process cascades down the plumbing system in a fraction of a second. It is a runaway feedback loop of explosive boiling. The eruption starts at a single point and spreads downwards, triggering the violent conversion of the entire reservoir of superheated water into a colossal volume of high-pressure steam. This is the geyser's eruption. The result is a continuous and powerful blast of steam and hot water that rockets out of the geyser's vent. The mixture is forced up the tube and through the constriction with incredible force. The constriction acts like the nozzle on a hose, focusing the energy into a powerful jet. The column of water and steam can be thrown hundreds of feet into the air. The roaring sound of a geyser eruption is the sound of this incredible release of energy, the sound of high-pressure steam escaping into the low-pressure atmosphere. The eruption will continue as long as there is enough superheated water in the system to fuel the chain reaction. It blasts out ton after ton of water, emptying the upper portions of its plumbing system. Eventually, the fuel begins to run out. The majority of the water that was in the system has been expelled. The pressure drops dramatically. Any remaining water continues to boil, but the eruption loses its force. The powerful jet of water subsides and is often replaced by a phase of pure steam. This is the steam phase, where the geyser simply roars like a giant fumarole, venting the last of the high-pressure steam from its deepest chambers. This phase can last longer than the water phase of the eruption. Finally, as the last of the pressure is spent and the system cools slightly, the roaring subsides. The eruption is over. The plumbing system is left empty and quiet, and the entire cycle, beginning with the slow recharge of cool groundwater, starts all over again. This detailed process explains the behavior of what we call a cone geyser, like Old Faithful. Its eruption is a relatively focused and steady column of water because its plumbing is a relatively simple tube with a constriction. However, there is another common type of geyser, known as a fountain geyser. Its mechanics are fundamentally the same, relying on the same chain reaction of flashing steam, but its surface expression is different due to a different plumbing structure. A fountain geyser, like the Grand Geyser in Yellowstone, does not have a cone built up around its vent. Instead, its vent is a wide pool of water at the surface. The plumbing system beneath this pool is still complex and still has a constriction deep down, but the wide open pool at the top changes the dynamic of the eruption. During the heating phase, you can often see large steam bubbles rising up through the pool and bursting at the surface. The eruption itself, when it happens, is not a focused jet. Instead, the explosive burst of steam happens from deep within the pool, blasting water outwards in a series of massive, star-shaped bursts. It looks less like a jet and more like a series of explosions from underwater. The eruption of a fountain geyser can be more chaotic and, for some, more spectacular than that of a cone geyser, throwing huge amounts of water in all directions rather than straight up. The underlying principle, however, remains exactly the same: the storage of energy in superheated water within a constricted plumbing system, and the release of that energy through a chain reaction triggered by a drop in pressure. The regularity of some geysers, like Old Faithful, is a testament to the stability of their underground heat source and plumbing. The rate at which the heat flows into the system is constant. The rate at which the plumbing refills with groundwater is also relatively constant. Therefore, the time it takes to heat the new column of water to the trigger point is also constant, leading to eruptions that occur at predictable intervals. However, most geysers are not regular. Their plumbing might be more complex, with multiple reservoirs that interact with each other. A small earthquake can shift the rock, slightly changing the shape of the plumbing, which can alter the geyser's eruption pattern, or even extinguish it completely. This is why the behavior of geysers can change over time. They are sensitive geological instruments, responding to subtle changes in the dynamic earth beneath them. So, let us review the entire mechanical process one final time, solidifying the sequence of events. First, the empty plumbing refills with cool groundwater after an eruption. Second, this new column of water is heated by the surrounding rock, with the water at the bottom becoming superheated due to the immense pressure from the water column above it. The constriction in the plumbing prevents this hot water from circulating and releasing its heat. Third, a few steam bubbles form in the superheated zone, rising up the plumbing. Fourth, these bubbles lift the water column, causing some of it to spill from the vent at the surface. Fifth, this loss of water reduces the weight of the column, causing a critical drop in pressure on the superheated water below. Sixth, this pressure drop triggers a chain reaction, a runaway cascade of violent boiling that converts the liquid water to a massive volume of steam. Seventh, this explosive expansion of steam powers the eruption, blasting the remaining water and steam high into the air. Finally, the system runs out of fuel, the eruption subsides, and the plumbing is left empty, ready to begin the cycle anew. This intricate dance of water, heat, and pressure, all dictated by the specific architecture of a hidden underground labyrinth, is what creates one of the most awe-inspiring spectacles in the natural world. It is a process of slow, patient accumulation of energy, followed by a sudden, violent, and complete release. Every eruption is a reminder of the immense power that lies just beneath the thin crust of the earth, a direct consequence of the great heat engine we first discussed. It is a perfect example of how a few simple physical principles, applied on a massive geological scale, can produce a result of breathtaking complexity and power. The geyser is a temporary valve for a planet's internal heat, a valve that is opened and closed by the water that falls from the sky. Part 4. The calm waters of hot springs and pools. In our previous discussion, we explored the violent and explosive mechanics of a geyser. We followed the intricate process of pressure buildup and catastrophic release, a story of confinement and eruption. We learned that a geyser is the result of a very specific and constricted underground plumbing system. Now, we will shift our focus entirely. We will turn away from the roaring jets of steam and water and turn towards their silent, peaceful neighbors. We will talk about the hot springs and the crystal clear, colored pools that are, for many, the most beautiful and mesmerizing features in all of Yellowstone. The fundamental question we must address is this: if the heat source deep underground is the same, and the water falling from the sky is the same, why are the results on the surface so dramatically different? Why does one feature erupt in a violent spectacle, while another sits in a state of apparent perpetual calm? The answer, once again, lies hidden from view, deep in the rock beneath our feet. The answer is the shape and nature of the plumbing. A hot spring is, in essence, a geyser that cannot erupt because its plumbing is too open. It lacks the critical feature that makes an eruption possible. It lacks the constriction. Imagine the plumbing of a hot spring not as a narrow, twisting tube with a bottleneck, but as a wide, open channel. It might be a large, vertical fissure in the rock that goes straight from the deep heat source to the surface. It could be a series of arc-wide, interconnected underground chambers that allow water to move freely between them. The key characteristic is a lack of any significant impediment to the movement of water. There is no narrow passage, no natural cork to trap the water and allow pressure to build. This simple difference in subterranean architecture is the root cause of the profound difference in surface behavior. The hot spring has a pressure release valve that is always open. Let us trace the journey of the hot, pressurized water from the deep reservoir as it makes its way to the surface through one of these open plumbing systems. The water, superheated to hundreds of degrees and rich with dissolved minerals, begins its ascent. Because the pathway is wide and unobstructed, the water can begin to rise as soon as it is heated. This upward movement is driven by a simple and elegant physical process called convection. Convection is the transfer of heat through the movement of a fluid, in this case, water. It is a continuous, cyclical process, and it is the engine that drives the calm and steady nature of a hot spring. We must understand this process in great detail to appreciate the tranquility of these pools. The process of convection begins at the bottom of the plumbing system, where the water is in contact with the hottest rock. As a parcel of water absorbs heat, its molecules begin to move faster and farther apart. The water expands slightly. This expansion means that the same amount of water now takes up a larger volume, which makes it less dense than the cooler water that is above it. Anything that is less dense than the fluid surrounding it will tend to rise. It becomes buoyant. Think of a piece of wood in water, or a hot air balloon in the cooler, denser air. The principle is exactly the same. So, this heated parcel of water at the bottom of the hot spring's plumbing begins a slow, silent journey upwards. It is not forced upwards by explosive steam. It simply drifts upwards, pushed by its own buoyancy. As this hot water rises through the wide, open channel, it carries its immense thermal energy with it. It travels up the fissure or through the large chambers, slowly moving towards the surface. When it finally reaches the top, it flows into the visible pool of the hot spring. Here, at the surface, the water is exposed to the much cooler air of the atmosphere. The temperature of the air might be 20 degrees Celsius, while the water arriving in the pool might be 90 degrees Celsius or even hotter. A rapid transfer of heat occurs. The hot water releases its energy into the air. We can see this heat release in the form of steam, the billows of white vapor that constantly rise from the surface of a hot spring. The water at the surface is giving up the heat it carried all the way from the deep earth. As the water at the surface releases its heat, it begins to cool down. The molecules slow down, move closer together, and the water becomes denser again. Now, being denser than the warmer water that is continuing to rise from below, this cooler surface water begins to sink. Gravity pulls it back down. It typically sinks along the cooler edges of the pool and the plumbing system, flowing downwards to replace the hot water that is rising in the center. This sinking water completes the loop. It travels back down to the bottom of the plumbing system, where it is once again brought into contact with the hot rock. It absorbs heat, becomes less dense, and begins to rise again. This entire process forms a continuous circular flow, a convection current. Hot water rises, releases its heat at the surface, cools, sinks, and then is heated again. It is a perfect, self-sustaining heat exchange system. This constant circulation is the secret to the hot spring's stability. It efficiently and continuously transports heat from the depths to the surface and releases it into the atmosphere in a gentle, controlled manner. The energy does not get a chance to build up. It is constantly being bled off. The system never reaches the critical point of explosive boiling that we see in a geyser. The pressure never builds to a catastrophic level because the open plumbing allows the convection cycle to operate without any hindrance. The water is free to move, and so the heat is free to escape. The result is a state of dynamic equilibrium, a feature that can remain in a state of calm, steaming beauty for centuries, all powered by this silent, circular dance of water. Let us now spend some time describing the physical appearance of a typical large hot spring, like those found in the Midway or lower geyser basins of Yellowstone. From a distance, the first thing you will notice is the steam. On a cold day, the plume of steam can be enormous, rising hundreds of feet into the air, looking like a cloud that is tethered to the ground. As you get closer, you see the pool itself, the most striking feature of many of the largest and hottest springs is the almost unbelievable clarity and color of the water. The water in the center of the pool is often a deep, brilliant blue. This blue is not caused by any pigment or dissolved mineral in the water. The water itself is colorless. The color is the result of the physics of light. When sunlight, which is made up of a spectrum of all colors, enters the deep, very pure water of the hot spring, it begins to interact with the water molecules. The water molecules are very good at absorbing the longer wavelengths of light, which are the red, orange, and yellow parts of the spectrum. However, the water molecules are not as good at absorbing the shorter, higher energy wavelengths, which are the blue and violet parts of the spectrum. Instead of being absorbed, this blue light is scattered. The water molecules bounce the blue light around, and some of it is scattered back up towards our eyes. So when we look into the deep center of a hot spring, the brilliant blue color we see is the light that the water has rejected. It is the same fundamental principle that makes the sky appear blue. The sky is blue because molecules in the atmosphere are better at scattering blue light from the sun than the other colors. A deep, pure body of water is one of the few places on Earth where we can see this same effect so vividly. The purity of the water is key. The water in these springs is so hot, often near boiling, that very few microscopic organisms can survive in it. This means there are no algae or suspended sediments to cloud the water and to interfere with the scattering of light. The water is exceptionally clear, allowing sunlight to penetrate deep into the pool, maximizing the scattering effect and producing the most intense shades of blue. Looking into one of these large pools is like looking into a window to another world. The water is so clear that you can see the rock formations and the sinter-coated walls of the pool's basin far below. The deep blue in the center, where the water is hottest and deepest, gradually gives way to lighter shades of turquoise and green as the water becomes shallower towards the edges of the pool. The edges themselves are often a brilliant white or a pale gray. This is the sinter deposit, the same mineral that lines a geyser's plumbing. As the hot water from the spring overflows its basin, it flows out in thin sheets across the surrounding ground. As this thin layer of water cools and evaporates, it can no longer hold all of its dissolved silica. The silica precipitates out of the solution and is deposited molecule by molecule, microgram by microgram, as a hard, permanent crust of sinter. This process of deposition is incredibly slow. Each overflow event leaves behind a layer of silica that is thinner than a sheet of paper. But over the course of thousands of years, these microscopic layers build up on top of each other, creating broad, terraced platforms of sinter that can extend for hundreds of feet around the main pool. These platforms are often covered in intricate, delicate patterns. The flowing water creates scalloped edges, tiny ridges, and rippled textures that look like frozen waterfalls of stone. The surface of this sinter can be smooth and polished in some places, and rough and porous in others. It is the physical record of the spring's history, a diary written in stone, showing the countless paths the overflowing water has taken over the millennia. The sound of a hot spring is also a study in contrast to the roar of a geyser. The primary sound is often a gentle, rhythmic lapping or pulsing. This is the sound of the convection current reaching the surface. The rising column of hot water creates a gentle bulge on the surface of the pool, which then overflows the rim in a steady, quiet pulse. It can sound like a slow, deep heartbeat. Accompanying this is the soft hiss of steam escaping the water's surface. Sometimes you may hear a deeper gurgling or a soft plopping sound. This is caused by bubbles of gas rising from the depths and bursting at the surface. These are the dissolved gases we mentioned earlier, carbon dioxide and others, which were trapped in the water under high pressure and are now being released as the water reaches the low pressure of the surface. But all of these sounds are gentle, quiet, and constant. They are the sounds of a system in balance, a system that is steadily and peacefully releasing its energy. Let us revisit the mineral that makes all of this possible: silica. The rock beneath Yellowstone is rhyolite, which is very rich in silica. The superheated water deep underground is an excellent solvent, and it dissolves a great deal of this silica, holding it in solution. This dissolved silica is what makes the sinter deposits, the geyser cones, and the strong lining of the geothermal plumbing. Without silica, the system would be very different. The plumbing would not be sealed, so pressure could not build in geysers. The beautiful formations around the hot springs would not exist. The very ground would be less stable. Silica is the building block of the Yellowstone geothermal world. The amount of silica that is being transported by this water is immense. It is estimated that the hot springs and geysers of Yellowstone collectively carry several tons of dissolved silica to the surface every single day. Over a year, this adds up to thousands of tons of rock being dissolved from the deep plumbing, transported to the surface by water, and redeposited as sinter. This is a powerful form of erosion, but one that happens completely out of sight. The landscape we see on the surface, the cones and terraces, is built from the rock that has been removed from the caverns and fissures miles below. The entire system is in a constant state of flux, of dissolving and redepositing, of reshaping itself from the inside out. The temperature of the hot springs can vary greatly. The hottest springs are the ones with the most direct and open connection to the deep heat source. Their water can be at or very near the boiling point for Yellowstone's high altitude, which is about 93 degrees Celsius. These are the springs with the clearest, deepest blue water because the intense heat prohibits almost all forms of life. Other springs may be cooler. Their plumbing might be longer and more circuitous, allowing the water to cool somewhat on its journey to the surface. Or they may be fed by a mixture of hot geothermal water and cooler, shallower groundwater. These cooler springs are often less clear, and their colors are different. Instead of the deep blue of scattered light, their colors are often produced by vast communities of microscopic organisms, a topic we will explore in great detail in the next part of our lecture. It is important to remember that every hot spring is unique. While they all operate on the same principle of convection through open plumbing, the specifics of that plumbing, its depth, its width, and its shape, will determine the exact temperature, size, and flow rate of the spring. Some are tiny, quiescent pools, just a few feet across. Others, like the Grand Prismatic Spring or the Excelsior Geyser Crater, are enormous cauldrons, hundreds of feet in diameter, discharging thousands of gallons of boiling water every minute. Excelsior is a particularly interesting case. It was once a massive geyser, erupting in columns 300 feet high in the 19th century. But a series of particularly violent eruptions are believed to have destroyed its constriction, effectively blowing out its own plumbing system. Since then, it has behaved as a massive hot spring, a testament to how a small change in the hidden underground structure can completely alter the nature of a feature. So, the calm we see on the surface of a hot spring is not a sign of inactivity. It is a sign of extreme, but very well-regulated activity. The convection current is moving an enormous amount of water and heat, constantly and efficiently. The tranquility of the pool belies the immense power of the geological engine that is feeding it from below. The hot spring is a window, not an engine itself. It is a window into the deep, hot, and dynamic world beneath Yellowstone. It allows us to see, through the clarity of its water, a glimpse of the rocky conduits below. It allows us to feel, in the warmth of its steam, the heat of the magma chamber far beneath, and it allows us to witness, in the steady overflow and deposition of minerals, the slow, patient, and unending process of geological change. To summarize this part of our discussion, the key difference between a violent geyser and a calm hot spring is the structure of its underground plumbing. A hot spring possesses a wide, open, and unobstructed pathway to the surface. This open structure prevents the buildup of pressure that is necessary for an eruption. Instead of storing and explosively releasing energy, a hot spring releases its energy continuously and gently through a process of convection. In this process, hot, less dense water rises from the depths, releases its heat to the atmosphere at the surface, and then cools, becomes denser, and sinks back down to be reheated. This continuous circulation creates the steady, stable nature of the spring. The visual beauty of the springs, their clear blue water, and intricate mineral deposits are direct results of this process. The blue color comes from light scattering in the pure, hot water, and the white sinter terraces are built over millennia from the dissolved silica that precipitates out as the water cools. A hot spring is a perfectly balanced system, a peaceful surface expression of the same immense planetary heat that powers the most violent geysers. It is a place of profound and deceptive tranquility. Deceptive because the calm is the result of a process of immense energy transfer, a silent and steady flow of heat from the heart of a volcano to the cool mountain air above. Part 5. The Colors of Life and Light. In the preceding parts of our lecture, we have constructed the fundamental machinery of Yellowstone. We have established the great heat engine, the magma chamber providing the thermal energy. We have followed the long, slow journey of water from the sky down into the crust where it becomes superheated. We then contrasted the two primary ways this energized water returns to the surface. We saw how a constricted, pressure-tight plumbing system creates the violent, episodic eruptions of a geyser, and we saw how a wide, open plumbing system allows for the calm, continuous circulation of a hot spring, a process driven by the gentle engine of convection. We described these hot springs as places of tranquility, their surfaces often steaming peacefully, their waters a deep and profound blue, and their edges rimmed with pale, hard minerals. But this is an incomplete picture. The story of these pools is not merely one of rock and water and heat. To stop there would be to miss the most visually spectacular element of all. Many of these springs and the runoff channels that flow from them are not just blue and white. They are painted with the most brilliant and vivid colors imaginable. They display bands of bright yellow, deep orange, rich red, and earthy brown, arranged in patterns that seem almost deliberately artistic. These colors are not random stains in the rock. They are not the result of unusual minerals in the water. These vibrant hues are the signature of life. They are the visible manifestation of immense, thriving communities of microscopic organisms, creatures that have adapted to survive and prosper in conditions of heat and chemical composition that would be instantly lethal to almost all other forms of life on Earth. This part of our lecture will be dedicated entirely to understanding the origins of these incredible colors. We will discover that the palette of a Yellowstone hot spring is created by two very different sources. First, we will re-examine the colors created by the fundamental physics of light and the basic geology of minerals. These are the colors of a lifeless world, the blues and the whites. Then, we will spend the majority of our time exploring the living rainbow, the colors created by biology. We will learn about the thermophiles, the heat-loving microbes that paint the landscape, and we will see how the simple, predictable cooling of water creates a living map of color, a biological thermometer written across the ground in shades of yellow, orange, and red. Let us begin with the colors of the non-living world. We will travel back to the edge of one of the great hot springs. For instance, the Grand Prismatic Spring, or the Sapphire Pool. We stand at the edge of the wooden boardwalk and look into the center of the pool. The first color that dominates our perception is the impossibly deep and vibrant blue of the water. As we mentioned in our last discussion, this color can be bewildering. It seems too pure, too intense to be natural. It is a color we associate with stained glass or tropical oceans, not with a boiling cauldron in the middle of the Rocky Mountains. The secret to this color is not what is in the water, but what the water itself does to the light that enters it. The water in the center of these large springs is exceptionally pure. It is so hot, often at or near the boiling point of 93 degrees Celsius, that it is essentially sterilized. Bacteria, algae, and suspended particles of silt or clay that would cloud normal bodies of water cannot survive here. The water is almost perfectly clear, just pure molecules of hydrogen and oxygen. This purity is the essential first ingredient for creating the color blue. The second ingredient is sunlight. Sunlight, which our eyes perceive as white or yellowish light, is in fact a mixture of all the colors of the rainbow. It is a spectrum of light waves. We can imagine these waves like waves on the ocean. Some waves are very long, with a great distance between their crests. Other waves are very short, with their crests packed closely together. In the spectrum of visible light, red and orange light have the longest wavelengths. Blue and violet light have the shortest wavelengths. All of these different wavelengths of light travel from the sun and enter the hot springs pool. Now, the interaction begins. The molecules of water are very, very good at absorbing certain types of light energy. Specifically, they are structured in a way that allows them to easily absorb the energy from the long wavelength light. So, as the sunlight penetrates into the pool, the red, orange, and yellow light is quickly absorbed by the water. Its energy is converted into a tiny amount of heat, and that color of light effectively disappears. It is subtracted from the sunlight. However, the water molecules are not good at absorbing the short wavelength blue light. They do not have the right structure to easily capture its energy. So, instead of being absorbed, the blue light is scattered. We can imagine this as the blue light waves bumping into the water molecules and being bounced off in all different directions. It is like throwing a bag of mixed-sized marbles into a dense forest of pins. The large marbles might get caught and stopped, but the small marbles will hit the pins and ricochet around in a chaotic fashion. The blue light ricochets around the pool, bouncing from water molecule to water molecule. A significant portion of this scattered blue light is bounced back upwards out of the water and into the eye of an observer standing at the edge of the pool. So, the color we see when we look into the deep part of the spring is the color that the water has rejected. It is the only part of the original sunlight that is able to make the journey down into the water and back out to our eyes. The other colors have been absorbed on the journey. The deeper and purer the water, the more pronounced this effect will be, resulting in a more intense and brilliant blue. This physical phenomenon, known as Rayleigh scattering, is the very same reason that our planet's sky is blue. The molecules of nitrogen and oxygen in the atmosphere are also much better at scattering short wavelength blue light from the sun than they are at scattering long wavelength red light. A deep hot spring is a microcosm of the sky, a pocket of atmospheric blue captured in water. Now let us shift our gaze from the center of the pool to its edges. Encircling the deep blue water, we often find a broad, pale ring of white or light gray rock. This is the second non-living color of the hot spring environment. This is the color of pure geology. This white material is the siliceous sinter, or geyserite, that we have discussed before. Let us review its formation one more time, but now with a focus on its color. The superheated water, deep underground, as it travels through the volcanic rhyolite rock, dissolves a large amount of the mineral silica. The hot, pressurized water is able to hold a great deal of this silica in a dissolved state. When the water reaches the surface in the hot spring, two things happen. It cools down, and the pressure on it is released. Both of these changes reduce the water's ability to hold dissolved silica. It becomes supersaturated. The silica can no longer stay in the water. It must come out of the solution and become a solid again. This process is called precipitation. As the water from the center of the spring overflows the rim of its basin, it spreads out in a thin sheet across the surrounding center terrace. This thin sheet of water cools very rapidly as it is exposed to the air. As it cools, the silica precipitates out, forming microscopic crystals of hydrated silicon dioxide. These tiny crystals are deposited on the ground, creating a new, infinitesimally thin layer of solid rock. This happens with every pulse of overflowing water, day after day, year after year, millennium after millennium. The layers build upon one another, creating the vast, intricate terraces that surround the pools. The color of this deposit, when it is pure, is a brilliant white. The individual silica crystals are colorless or translucent, but when they are packed together in a porous, fine-grained mass, they scatter light of all colors equally, which our eyes perceive as white. It is the same reason that snow and sugar are white. The stark whiteness of the center provides a stunning contrast to the deep blue of the water, creating a landscape that feels both alien and beautiful. Sometimes, trace amounts of other minerals dissolved in the water, such as iron or manganese, can become trapped in the center as it forms, staining it with subtle shades of gray, cream, pink, or light brown. But the dominant geological color, the blank canvas upon which life will paint, is the pure white of the silica. So we have our two foundational colors, the blue of scattered light and the white of precipitated minerals. This is the appearance of a sterile, boiling hot world, but very few springs in Yellowstone are entirely sterile. Life is tenacious, and in the slightly cooler waters away from the main vent, life has found a way not just to survive, but to thrive in the most spectacular fashion. And it is this life that creates the brilliant yellows, oranges, and reds that make the springs so famous. The organisms responsible for these colors are called thermophiles. The name itself tells us their story. In Greek, thermos means heat, and phile means lover. These are the heat lovers. They are microorganisms, single-celled creatures so small that millions of them can exist in a single drop of water. They are some of the most ancient forms of life on our planet, belonging to the domains of life we call bacteria and archaea. These are not the germs that make us sick. These are extremophiles, specialists that have evolved over billions of years to live in environments that we would consider hellish. The key to understanding how these thermophiles create the stunning color patterns is to understand the concept of a temperature gradient. Let us return to our large hot spring. The water emerges in the center of the pool at its hottest temperature, let us say 93 degrees Celsius. From the center, the water flows outwards in all directions, spilling over the rim and running in shallow channels across the center terrace. As this water flows away from its source, it steadily cools. Just a few feet from the main pool, the temperature might have dropped to 85 degrees. 10 feet away, it might be 75 degrees. 50 feet away, it might be 60 degrees. And so on. The further the water gets from its source, the cooler it becomes. This creates a predictable and stable map of different temperatures. You can think of it as a series of concentric rings or zones, each with its own specific and constant temperature. Each one of these temperature zones provides a unique habitat, a distinct environment, and each one of these habitats is colonized by a different type of thermophile, one that is perfectly adapted to live at that exact temperature. The thermophiles themselves have color because they contain pigments. Pigments are molecules that absorb certain wavelengths of light and reflect others. The color we see is the color of the light that is reflected. The plants in your garden are green because they contain a pigment called chlorophyll, which is very good at absorbing red and blue light for photosynthesis, but reflects green light. The thermophiles in Yellowstone also have pigments. Many of them do perform photosynthesis, so they have chlorophyll. But they also have another very important class of pigments called carotenoids. Carotenoids are responsible for the yellow, orange, and red colors we see in carrots, autumn leaves, and flamingos. In the thermophiles, these carotenoid pigments serve two crucial functions. First, they act as a sunscreen. The water in the runoff channels is shallow and clear, and the high altitude of Yellowstone means the sunlight is incredibly intense and rich in damaging ultraviolet radiation. The carotenoid pigments absorb this harmful radiation, protecting the cell's delicate internal machinery, including its chlorophyll. Second, they can help the organism to capture more light energy for photosynthesis, absorbing wavelengths of light that chlorophyll cannot. The beautiful color patterns we see are the result of different species of thermophils, each with a different ratio of chlorophyll to carotenoid pigments living in their preferred temperature zone. Let us now take a slow walk away from the central pool, moving down the temperature gradient, and examine the life and color we find in each zone. Our journey begins in the water that is just leaving the main spring. The temperature here is extremely hot, from the boiling point of 93 degrees down to about 73 degrees Celsius. This is the upper limit for photosynthetic life. It is a brutal environment. The water is scalding hot, and the sunlight is intense. Only the toughest of the tough can survive here. The dominant organisms in this zone are a group of bacteria called Cenococcus. These bacteria are packed with yellow-colored carotenoid pigments. They still have the green pigment chlorophyll to make their food, but the yellow carotenoids are so abundant that they completely mask the green color. It is like having a green sheet of paper and scribbling all over it with a bright yellow crayon. The color you will see is yellow. The Cenococcus grow together in the vast colonies, forming a thick, slimy layer on the center rock called a microbial mat. These mats are often stringy and filamentous, with the long strands of bacteria aligned in the direction of the water flow. So the first band of color we encounter in the hottest water that can support this type of life is a brilliant, vibrant yellow. Now, we move a little further away from the spring, into a zone where the water has cooled slightly. The temperature here is now between roughly 73 and 65 degrees Celsius. This range is just a little too cool for the yellow-producing Cenococcus to dominate, but it is the perfect temperature for a different community of microbes. These organisms are also photosynthetic bacteria, but they have a different mixture of pigments. Their carotenoids produce a deep orange color. Again, they have green chlorophyll, but it is completely hidden by the more dominant orange sunscreen pigments. As a result, the yellow band gives way to a distinct band of brilliant orange. The microbial mats here might be thicker and have a different texture, perhaps more clumpy or rubbery than the filamentous yellow mats. We are seeing a direct visual representation of a change in the dominant species of life, all dictated by a simple drop of a few degrees in water temperature. We continue our walk, following the ever-cooling water. We now enter a zone where the temperature ranges from about 65 down to 55 degrees Celsius. Once again, the community of life changes. The orange bacteria cannot compete as well here. This zone is often dominated by yet another set of bacteria, and sometimes archaea, that produce a deep, rusty red or a rich brown color. The red color is again produced by specific carotenoid pigments. In some cases, the brown color can come from organisms that are not photosynthetic. Instead of getting their energy from sunlight, they get their energy from chemical reactions, a process called chemosynthesis. Some of these organisms get energy by oxidizing iron or sulfur compounds that are dissolved in the water, and their waste products can be brownish. This zone is often a complex mixture of different species, a mosaic of reds and browns that marks another step down the thermal ladder. The mats here can be very thick, forming dense, leathery sheets over the center. Finally, we reach the outermost edges of the runoff channel. The water here has traveled a long way from its boiling source and has cooled considerably to temperatures below 55 degrees Celsius. In this much more temperate environment, the intense sunlight is less of a threat, and the heat stress is greatly reduced. Here, a new set of organisms can finally thrive, including various types of algae. Algae are more complex than the bacteria that dominate the hotter zones, and in these milder conditions, they do not need to produce as much of the protective carotenoid sunscreen. As a result, their green chlorophyll is no longer masked. It becomes the dominant visible pigment. So, the final color band we see at the coolest end of the thermal gradient is a deep, rich green or a dark greenish brown. This is a color we are more familiar with, the color of plant life in ponds and streams all over the world. Its appearance here signifies that the water has finally cooled to a point where it can support more conventional forms of life. So, when we look at a feature like the Grand Prismatic Spring from above, what we are seeing is a perfect bullseye of life, a living thermometer. In the center, we have the sterile blue of pure, boiling water, a color from physics. Surrounding it, we have the white ring of pure mineral deposits, a color from geology. And then, radiating outwards, we have the living rainbow. The first ring of life is the bright yellow of the most heat-tolerant bacteria. This is followed by the deep orange of a slightly less heat-tolerant community. Then comes the rich red and brown of the next community in line. And finally, the dark green of the algae and other organisms at the coolest outer edges. Each colored band is a distinct ecological zone, a neighborhood defined by temperature and populated by the unique forms of microbial life that are adapted to thrive in those precise conditions. It is a stunningly direct and beautiful visualization of evolution and adaptation. This entire living system is a mat. The term microbial mat is key. It is not just a thin stain on the rock. It is a complex, layered community. The top layer is dominated by the photosynthetic bacteria, which form a canopy capturing the sunlight. Beneath them, in the layers that receive no light, live other types of microbes. These are the decomposers and the recyclers. They feed on the waste products and the dead cells of the photosynthesizers above them. They break down complex organic molecules and return the basic chemical building blocks to the system so they can be used again by the primary producers on the top layer. The mat is a self-contained, self-sustaining ecosystem with its own food web and nutrient cycles, all packed into a slimy, colored layer that might be only a few centimeters thick. It is a tiny, ancient world, powered by sunlight from above and geothermal heat from below. The beauty of these colored mats is fragile. The boardwalks in Yellowstone are not just for visitor convenience. They are essential for protecting these delicate features. A single footstep off the boardwalk could crush a section of the microbial mat that has taken centuries to form. It can also break through the thin cinder crust, releasing scalding water and potentially creating a new, unsafe hot spring. The colors and patterns are a product of a very specific and stable flow of water. If that flow is altered, if a channel is blocked or diverted, the temperature gradient will change, and the entire colored pattern will change with it. The communities of microbes will die off in one area and colonize a new one, always following their preferred temperature. The living rainbow is in a constant state of slow, subtle flux, always redrawing itself in response to the slightest changes in the Earth's plumbing. In summary, the vibrant colors that adorn Yellowstone's hot springs are a profound story told in 3 parts. There is the physics of light, which scatters through pure, deep water to create an ethereal blue. There is the geology of the Earth, which dissolves and redeposits minerals to lay down a canvas of stark white sinter. And most spectacularly, there is the biology of ancient life, the thermophilic microbes that have adapted to this extreme world. These tiny organisms, with their protective pigments of yellow, orange, and red, arrange themselves in precise communities along the temperature gradients of the cooling water, creating a living rainbow. Looking at a Yellowstone hot spring is therefore not just looking at a pool of hot water. It is looking at a complete and complex ecosystem. It is a window into what life might have looked like on the early Earth before the evolution of plants and animals. And it is a stunningly beautiful reminder that life can find a way to flourish in the most unlikely and inhospitable corners of our world, painting the sterile rock with the brilliant colors of its own resilience. Part 6. Vents, steam, and bubbling mud. Up to this point in our comprehensive exploration of Yellowstone's geothermal wonders, our focus has been centered on water in its liquid state. We have delved into the explosive dynamics of geysers, where columns of superheated water erupt with tremendous force. We have also examined the serene beauty of hot springs, where the same superheated water circulates calmly in pools of brilliant blue, surrounded by terraces of white mineral and vibrant mats of microscopic life. In both of these cases, the defining feature is the presence of a significant and visible body of liquid water at the surface. However, the geothermal system of Yellowstone is not limited to these water-centric expressions. The immense heat engine beneath the park manifests itself in other ways, creating features that are just as fascinating, though perhaps less conventionally beautiful. These are the features that arise when the balance between heat and water is different. Specifically, they occur in places where there is an abundance of heat, but a very limited supply of water. In this part of our lecture, we will turn our attention to these drier, steamier, and muddier members of the geothermal family. We will investigate the fumaroles, which are vents that hiss with pure steam, and we will explore the mud pots, which are acidic hot springs that have transformed the surrounding rock into a bubbling, gurgling cauldron of hot clay. By understanding these features, we will complete our picture of the many varied ways that the planet's internal heat can escape to the surface. Let us begin with the simplest and most direct of all geothermal features, the fumarole. A fumarole, also known as a steam vent, is nothing more than a crack or a hole in the ground from which hot gases escape. It is the most basic possible expression of geothermal activity. A fumarole represents a direct pathway from the deep, hot regions of the Earth's crust to the surface, but a pathway that does not intersect with a significant source of groundwater. Imagine the complex plumbing system we described for geysers and hot springs. Now, imagine a similar set of fractures and fissures, but in an area where very little surface water is able to percolate downwards. The heat from the magma chamber is still present, radiating upwards and heating the rock to extreme temperatures. Any small amount of groundwater that does find its way down into these hot zones is instantly flashed into steam. Furthermore, the magma itself, deep below, is constantly releasing gases. As the molten rock cools and crystallizes, gases that were dissolved within it, such as water vapor, carbon dioxide, and hydrogen sulfide, are exsolved, meaning they come out of the solution. These magmatic gases, along with the steam from the boiled groundwater, rise up through the cracks in the rock. With no column of liquid water to block their path, these gases can travel directly to the surface and vent into the atmosphere. This is a fumarole. The appearance of a fumarole is often subtle from a distance. You might see what looks like a patch of ground from which a constant plume of steam is rising, as if a small campfire were burning there. As you get closer, you begin to hear it. The sound of a fumarole can be a gentle hiss, like air slowly leaking from a tire, or it can be a deafening roar, like a jet engine. The volume and intensity of the sound depend on the size of the vent and the pressure of the escaping gases. The steam itself is often invisible right at the mouth of the vent, because it is superheated and has not yet condensed into visible water droplets. A few inches above the ground, as it mixes with the cool air, it condenses into the familiar white cloud of steam that we can see. The ground immediately surrounding the opening of a fumarole is often altered by the heat and the chemical nature of the gases. The area can be barren of vegetation, as the soil is too hot for plants to survive. The rocks can be stained with bright yellow mineral deposits. This yellow coloring is often pure sulfur. One of the gases commonly found in geothermal steam is hydrogen sulfide, which has the distinct and unpleasant smell of rotten eggs. When this hot hydrogen sulfide gas meets the oxygen in the atmosphere at the vent, a chemical reaction can occur that deposits solid, crystalline sulfur around the opening. These bright yellow sulfur deposits, called sulfaturous, are a clear sign of an active fumarole. Fumaroles are the hottest of all the geothermal features in Yellowstone when measured right at the vent. While the water in a hot spring is limited by its boiling point, which is about 93 degrees Celsius at this altitude, the steam escaping from a fumarole is not. It can be much hotter, often reaching temperatures of 130 degrees Celsius or even higher. This is because it is dry steam, not steam that is in contact with liquid water. Standing near a large, roaring fumarole can be an intimidating experience. The ground often vibrates from the force of the escaping steam, and the heat can be felt from many feet away. You are witnessing a direct and unfiltered release of the Earth's internal energy. Fumaroles can be found scattered throughout all the geyser basins, but they are particularly common in areas of higher elevation or on the slopes of hillsides, places where the groundwater table might be deeper and less likely to flood the steam vents. The Norris Geyser Basin is particularly famous for its powerful and loud fumaroles, contributing to its reputation as the hottest and most dynamic basin in the park. A fumarole is a sign of a very hot but very water-starved system. It tells us that the magma chamber is close, the rock is intensely hot, but the plumbing is not filled with water. It is a dry heat. But what happens if the situation is not completely dry? What if there is some water available at the surface, but not enough to create a full-fledged hot spring? What if the ground is saturated with rainwater and snowmelt, but there is no large reservoir of groundwater to feed a deep, clear pool? This is the recipe for creating a mud pot. A mud pot is, in essence, a hot spring that is so starved of water that it has become a thick slurry of mud and clay. But the process of its creation is more complex and interesting than that simple description might suggest. The story of a mud pot is a story of acid and the slow, inexorable dissolution of solid rock. The creation of a mud pot begins with a feature that is very much like a fumarole. There is a heat source deep below and a pathway for steam and other gases to reach the surface. The critical difference is the location. A mud pot forms in a place where the surface ground is composed of soft, clay-rich soil or easily decomposed rock, and where a shallow basin or depression allows a small amount of surface water from rain and snow to collect. This water does not fill the geothermal plumbing. It simply sits on top of it, creating a shallow, stagnant pool. Now, the geothermal gases begin to rise from below, just as they would in a fumarole. The most important of these gases for the creation of a mud pot is hydrogen sulfide, the gas that smells of rotten eggs. As the bubbles of hydrogen sulfide gas rise up and enter the shallow pool of surface water, a fascinating biological and chemical process begins. Living in this water are specialized microorganisms, another type of extremophile. These microbes are not photosynthetic. They do not get their energy from the sun. They are chemosynthetic, meaning they get their energy from chemical reactions. Specifically, these microbes get their energy by consuming the hydrogen sulfide gas. They metabolize it. The waste product that they excrete is sulfuric acid. Over time, this process turns the shallow pool of water into a pool of strong acid. The microbes are constantly converting the endless supply of hydrogen sulfide from below into sulfuric acid, making the water as acidic as lemon juice or even stomach acid. Now this powerful acid goes to work. The acid begins to attack the surrounding rock and the clay minerals in the soil at the bottom of the pool. The sulfuric acid is a potent solvent, and it slowly but surely breaks down the solid rock, dissolving it and transforming it into fine particles of silica and clay. The hard volcanic rhyolite is reduced to a soft, gooey, bubbling slurry. The rock is literally being digested by the acidic water and the microbes that live within it. This is what a mud pot is. It is a basin of rock that has been dissolved from the top down by a self-sustaining acid factory, powered by gas from below and operated by a community of specialized microbes. The appearance of a mud pot is completely different from a clear hot spring. There is no blue water, no beautiful center terrace. Instead, you see a pool of viscous, bubbling mud. The consistency of the mud can vary greatly. In the spring, when there is a lot of meltwater, the mud pots are often thinner and more fluid, like a bubbling pot of hot soup or a simmering vat of watery paint. They will bubble and splash vigorously. As the summer progresses and the weather becomes drier, the water evaporates and the mud becomes thicker. It might take on the consistency of thick oatmeal or wet cement. The bubbling action becomes much slower and more dramatic. Large, thick bubbles of gas will slowly rise to the surface, swell into a large dome of mud, and then burst with a deep, resonant plop or gloop sound, splattering thick mud in all directions. The sound of a field of active mud pots is one of the strangest in Yellowstone, a constant chorus of wet, gurgling, and plopping noises. The color of the mud pots is also distinctive. They are typically not the brilliant whites or yellows of other features. Instead, they are usually shades of gray, brown, and sometimes pink. The gray color comes from the decomposed rock itself. The fine clay and silica particles, when mixed with water, form a gray slurry. The various shades of brown, pink, or even reddish tones are caused by the presence of different iron compounds in the original rock. As the rock is dissolved by the acid, these iron compounds are released and oxidized, essentially rusting, which stains the mud with these earthy colors. The fountain paint pots in the lower geyser basin are a particularly famous example of this, with mud pots that display a range of colors, from pearly gray to a delicate pink, often swirling together in hypnotic patterns as the mud convects and bubbles. The bubbling action in a mud pot is driven by the same force as a fumarole, the constant rising of steam and other gases from the hot source below. The mud itself is not boiling. The temperature of the mud is usually a bit below the boiling point. The bubbles are not steam bubbles, formed by the boiling of the mud itself. They are bubbles of gas that have traveled a long way from the deep earth and are simply passing through the thick mud on their way to the atmosphere. The mud is just a passive medium that is being agitated by this constant flow of gas from below. You can think of it like blowing air through a straw into a thick milkshake. The milkshake itself is not boiling, but it will bubble and churn because of the air you are forcing through it. The mud pot is the same, but the straw is a crack in the earth, and the breath is the hot, gas-rich steam from a volcanic system. The convection that happens in a clear hot spring also happens in a mud pot, but it is much slower and more viscous. Hotter, less dense mud from the bottom slowly rises, while cooler, denser mud from the surface sinks, creating slow, swirling patterns on the surface. So, let us summarize the key differences that lead to these varied features. If you have a great deal of heat and a great deal of water in a constricted plumbing system, you get a geyser. If you have a great deal of heat and a great deal of water in an open plumbing system, you get a hot spring. If you have a great deal of heat but very little water, you get a fumarole, a dry vent of hissing steam. And if you have a great deal of heat, a limited and shallow supply of surface water, and hydrogen sulfide gas, you get a mud pot, an acidic cauldron where rock is actively being dissolved into bubbling clay. Each one is a different expression of the same underlying geothermal processes, a different answer to the question of how heat and water interact under the specific geological conditions of a particular location. These drier features play an important role in the overall ecosystem and geology of Yellowstone. Fumaroles and mudpots are major sources of the gases that give Yellowstone's air its distinctive sulfurous smell. They are also important sites of mineral alteration. The acidic conditions created by these features are a powerful geological force, constantly breaking down the hard volcanic rock and turning it into soft clay. This process helps to create the unique soils and landscapes found in the geothermal basins. The ground in these areas is often unstable and soft, a direct result of this ongoing acid attack from below. It is a landscape that is actively being unmade and remade. One of the best places to witness this full spectrum of features is the Fountain Paint Pots area. A short walk on the boardwalk there will take you past all 4 major types of geothermal features. You will see clear, blue hot springs, like Silex Spring. You will see small, sporadically erupting geysers, like Fountain Geyser or Clepsydra Geyser. You will see hissing fumaroles, venting steam from the hillside. And of course, you will see the famous paint pots themselves, the bubbling mud pots of gray and pink clay. It is a compact and perfect lesson in geothermal geology, showing how subtle changes in the water supply and gas chemistry can create a remarkably diverse array of natural wonders, all within a few hundred feet of each other. In conclusion, our journey through Yellowstone's geothermal world would be incomplete without an appreciation for these less watery, but no less dynamic, features. The fumaroles are the raw, direct voice of the volcano, a release of pure heat and gas from the deep earth. They are simple, powerful, and hot. The mudpots are a more complex and alchemical story. They are places of transformation, where gas, water, microbes, and rock combine to create a bubbling, acidic brew that actively digests the landscape. They are a reminder that the geothermal forces are not just about heat and pressure, but also about powerful chemistry. Together, the steam vents and the bubbling mud complete the family portrait of Yellowstone's geothermal activity. They show us what happens at the dry and acidic end of the spectrum, providing a crucial contrast to the water-drenched worlds of geysers and hot springs, and giving us a fuller and more nuanced understanding of the many ways a planet can vent its internal fire. Part 7. A walking tour of the Great Geyser Basins. For the past several hours, we have been building a foundation of knowledge. We have journeyed deep into the earth to understand the great heat engine that is the Yellowstone hotspot. We have followed the centuries-long path of a single drop of water as it fell from the sky and seeped miles into the crust to become superheated. We have meticulously dissected the mechanics of a geyser's eruption, contrasting its violent release of energy with the steady, calm circulation of a hot spring. We have marveled at the microscopic life forms that paint the landscape in a rainbow of living color, and we have explored the drier, more acidic features like hissing steam vents and bubbling pots of mud. We have learned the why and the how. Now, in this part of our lecture, we will explore the where. We will take all of this theoretical knowledge and apply it to the real world, to the actual landscape of Yellowstone National Park. We will embark on a slow, virtual walking tour. We will travel through the major geyser basins of the park, starting in the south and moving north. We will observe the famous features and the smaller, quieter ones. And with each one we see, we will pause and remind ourselves of the deep geological processes that are responsible for its existence. This is where all the pieces of our story come together. Imagine yourself there now. The air is cool and crisp, carrying the scent of pine needles and the faint, unmistakable smell of sulfur. You are standing on a boardwalk made of weathered wood, and all around you, the ground is alive. Steam rises in ghostly plumes from 100 different vents. The earth hisses, gurgles, and bubbles. We will begin our journey in the most famous and concentrated collection of geothermal features on the entire planet, the Upper Geyser Basin. The Upper Geyser Basin is a relatively small area, only about 2 square miles, but packed within it is the largest single concentration of geysers in the world. This is the home of Old Faithful, and it is here that our tour begins. Before we even see the geyser itself, we feel its presence. We are walking on the boardwalk that winds along the banks of the Firehole River. The river itself is a thermal feature. Its water is a mixture of cool mountain runoff and the scalding hot discharge from hundreds of springs and geysers. Steam rises from the river's surface, especially on a cool morning. The scene is set. We round a bend, and there it is. Not the eruption, but the geyser's cone. The cone of Old Faithful is a low, broad mound, a gentle hillock of pale, grayish-white rock. This mound is made of siliceous sinter, or geyserite. We must remember how it was built. For thousands of years, with every single eruption, hot water loaded with dissolved silica has been blasted out of the ground. As this water has cascaded down the sides of the mound and cooled, the silica has precipitated out, depositing a paper-thin layer of new rock. The entire mound we are looking at is the accumulated result of countless eruptions, a monument built by the geyser itself, microgram by microgram, over an immense span of time. We find a spot on one of the long wooden benches that face the geyser, part of a large, semicircular viewing area. We are waiting. This is a significant part of the geyser experience, the quiet anticipation. The geyser is calm right now. A steady plume of steam rises from the opening at the top of the cone, but there is no water visible. The system is in its recharge and heating phase. Deep below our feet, a complex network of fissures and chambers is slowly refilling with groundwater. This water is being heated by the surrounding rock, which is in turn heated by the great magma chamber miles below. The water at the bottom of this hidden system is becoming superheated, held in a liquid state by the immense pressure of the water column above it. As we sit and watch, we might begin to see the first signs of the coming eruption. Small splashes of water begin to appear at the vent. These are the preliminary surges. We now know exactly what is causing them. Deep in the plumbing, the first bubbles of steam have begun to form in the superheated water. These buoyant bubbles rise, and like pistons, they push the water at the top of the column upwards and out of the vent. Each splash tells us that the process is accelerating, that the system is approaching its critical point. The splashing becomes more frequent, more energetic. Then, the eruption begins. It starts not with a roar, but with a sudden, powerful surge. A column of water and steam shoots 50 feet into the air, then another, higher. Then, with a deep, rushing roar, the full eruption is unleashed. A powerful, sustained jet of boiling water and steam rockets upwards, reaching a height of 100, 150, sometimes close to 180 feet. The column of water is not perfectly steady. It pulses and sways in the wind, a magnificent, shimmering tower of white against the blue sky. We must remember the chain reaction we discussed. This incredible display is being powered by a runaway cascade of flashing steam. The initial splashes reduce the pressure in the system, triggering explosive boiling deep below. This boiling ejected more water, which further reduced the pressure, causing even more violent boiling deeper down. The roar we hear is the sound of a massive volume of superheated liquid, instantaneously converting into an even more massive volume of high-pressure steam, a process that is tearing its way down the geyser's plumbing and forcing its entire contents up and out through the narrow constriction near the surface. The eruption continues for several minutes. It is a spectacle of immense power, a direct and awesome release of planetary energy. We can feel the fine mist on our faces, and the air is thick with the clean mineral scent of the steam. Gradually, the water phase of the eruption subsides. The jet becomes less powerful, containing more steam than water. The geyser has expelled most of the liquid from its upper plumbing. The eruption then transitions into the steam phase. The deep roaring continues, sometimes even louder than before, as the geyser vents a massive, billowing cloud of pure steam. This is the last of the high-pressure gas escaping from the deepest parts of the system. This steam phase can last for several minutes more, a final, powerful exhalation before the system falls quiet. Then it is over. The roaring stops. A gentle plume of steam is all that remains. The ground is soaked, and the Firehole River has received thousands of gallons of hot water. Deep below, the cycle begins anew. The empty chambers start to refill with cooler water, and the slow process of heating starts all over again. The famed regularity of Old Faithful is a testament to the stability of its underground system. Its plumbing is not easily changed, and its source of heat and water is remarkably consistent, allowing the cycle of recharge and heating to take a predictable amount of time, leading to an eruption roughly every 90 minutes. Our tour does not end here. We leave the benches at Old Faithful and begin a walk along the boardwalk that winds its way through the rest of the Upper Geyser Basin. This is Geyser Hill, a landscape dotted with dozens of thermal features. We walk past smaller geysers, like Anemone Geyser. Anemone is a tiny fountain geyser, a small pool that erupts every 5 to 10 minutes in a bubbly splash that reaches only a few feet high. It is a perfect miniature model of the process we just witnessed on a grand scale. Its plumbing system is much smaller and shallower, so it recharges and heats very quickly, allowing for its frequent, small eruptions. As we walk, we are surrounded by pools of startlingly clear blue water. These are hot springs. We look down into one, called Blue Star Spring. The color is an intense sapphire. We remind ourselves that this is the color of physics. The water is nearly boiling, sterile and pure. The blue light from the sun is being scattered by the water molecules and reflected back to our eyes, while all other colors are absorbed. The water is not blue. It is making the light blue. The edges of the pool are coated in a delicate, scalloped crust of white sinter, the mineral signature of the hot, silica-rich water. We continue our walk, heading towards some of the other giants of this basin. We approach a large, seemingly empty pool. This is the home of Grand Geyser, the tallest predictable geyser in the world. It is a fountain geyser, not a cone geyser. Its eruptions do not come from a raised cone, but from this wide, open pool. When it erupts, it is not a focused jet, but a series of massive, star-shaped bursts of water that can reach 200 feet in height. This different eruption style is due to its different plumbing. The explosive release of steam happens from deep within the large pool, blasting the water outwards in all directions. Predicting its eruption is a fine art, often linked to the activity of a smaller, adjacent spring called turbine geyser. When turbine geyser begins to pulse and overflow in a certain way, it signals that the entire complex underground system is pressurized and ready, and an eruption of ground is likely to occur soon. Further along the path, we encounter a feature that looks like an ancient, ruined fortress. This is Castle Geyser. It has one of the largest and oldest cinder cones in the entire park. The cone is a gnarled, massive structure, gray and lumpy, a testament to its immense age. Scientists estimate that this cone has been building for thousands of years, layer by slow layer. When Castle erupts, it is a powerful but messy affair. A column of water shooting 70 or 80 feet high from the top of the ancient structure. But what is most impressive about Castle is its steam phase. After the water phase ends, Castle Geyser roars with the sound of a freight train for 30 to 40 minutes, releasing a gigantic and continuous column of steam. Its deep, complex plumbing holds an enormous amount of energy, and it takes a very long time to vent it all. Our walk through the upper basin concludes at a pool that is both beautiful and tragic. We arrive at Morning Glory Pool. Decades ago, this pool was famous for its stunningly clear, deep blue water, resembling the flower for which it was named. Today, the pool is still beautiful, but its colors have changed. The center is now a greenish yellow, and the edges are a brilliant orange. This change is not a natural process. It is the result of human carelessness. For years, people threw coins, trash, and rocks into the pool. This debris has begun to clog the vent at the bottom of the pool, partially blocking the flow of hot water from below. This obstruction has lowered the overall temperature of the pool. And here, we must apply our knowledge from Part 5. We know that the colors in a spring are a direct result of temperature. The original, very hot water was too hot for most microbes, so the pool was a pure, physical blue. Now that the temperature has dropped, it has allowed thermophils, the heat-loving microbes, to colonize the pool. The yellows and oranges we now see are the colors of the microbial mats that have grown in the newly cooled water. The pool is still beautiful, but it is a beauty born of damage. It is a living thermometer that is showing us, in vivid color, the consequences of disturbing a delicate geological system. We leave the upper basin and travel a few miles north. Our next stop is the Midway Geyser Basin. The scale here is different. There are fewer individual features, but they are immense. We park and walk onto a bridge that crosses the Firehole River. The air is thick with steam, so much so that visibility can be limited. The entire river is steaming because a colossal amount of boiling water is being discharged into it from this basin. The volume of water and energy being released here is staggering. Our first sight after crossing the bridge is a vast, steaming crater, a pool several hundred feet across. This is the Excelsior Geyser Crater. This feature was once the most powerful geyser on Earth, erupting in the 1880s in titanic blasts that reached 300 feet high. But its eruptions were too violent. They literally blew the geyser apart, shattering its internal plumbing system. and destroying the constriction that was necessary for eruptions. Since then, Excelsior has acted as a massive hot spring. It is no longer a geyser, but a gaping wound in the earth, pouring more than 4,000 gallons of boiling water per minute into the Firehole River. It is a stark reminder of the incredible power simmering just below the surface and the dynamic, ever-changing nature of these features. Next to Excelsior is the main attraction of the Midway Geyser Basin and one of the most photographed features in all of Yellowstone. This is the Grand Prismatic Spring. It is the largest hot spring in the United States and the third largest in the world. From the ground level boardwalk, its sheer size is hard to comprehend. It is a vast expanse of steaming water over 370 feet in diameter. The steam is so thick that it often obscures the far side of the pool, creating a surreal, otherworldly atmosphere. To truly appreciate this feature, we must imagine ourselves at the viewpoint on the nearby hillside, looking down upon it. From this vantage point, the full glory of the spring is revealed, and it is here that we must apply our knowledge of light, geology, and microbiology in the greatest detail. From above, the Grand Prismatic Spring is a perfect, gigantic bullseye of impossible color. In the very center lies the deep, sterile heart of the spring. The water here is at its hottest, well above the survival limit for even the most extreme thermophiles. The color is a profound and brilliant blue. This is the blue of Rayleigh scattering. The sunlight entering the deep, pure water is being stripped of its red, orange, and yellow wavelengths, which are absorbed, leaving only the blue light to be scattered back to our eyes. It is the color of absolute purity and intense heat. Surrounding this blue core is a narrow ring of pale green or yellow-green. This is the first zone of life. The water here has cooled just enough to a temperature between 73 and 85 degrees Celsius to allow the most heat-tolerant photosynthetic bacteria to survive. These are the Synechococcus bacteria. They are filled with yellow carotenoid pigments that act as a sunscreen, masking their green chlorophyll. This is the yellow band on our living thermometer, moving outwards from the yellow ring. The water in the broad, shallow runoff plain continues to cool. The next band of color we see is a breathtakingly brilliant orange. This is a zone where the temperature is lower, perhaps between 65 and 75 degrees. This temperature is ideal for a different community of microbes. These bacteria are packed with orange-colored carotenoid pigments, which completely dominate their appearance. The change from yellow to orange signifies a distinct and predictable shift in the dominant species of life, all dictated by the simple cooling of the water as it flows away from its source. Beyond the orange band, the water cools further, and the color transitions to a deep, rusty red, and then to a dark, earthy brown. This zone, with temperatures below 65 degrees, is home to yet another suite of microorganisms. Some are photosynthetic, with red pigments. Others are chemosynthetic, deriving energy from minerals and contributing to the brownish hues. This is the red and brown band of our thermometer. Finally, at the outermost edges of the feature, where the water has cooled significantly, the harsh conditions have subsided. Here, the green of algae and other, more common organisms can finally appear. This is the cool, green edge of the thermal world. Encircling this entire living rainbow is the stark white and gray of the mineral terrace. The center deposited by the overflowing water. The Grand Prismatic Spring is the ultimate expression of the principles we have learned. It is a single, magnificent feature that displays the colors of physics, the colors of geology, and the entire living spectrum of microbiology, all laid out on a gigantic scale. Our journey continues north to the Lower Geyser Basin. This is a vast area with a great variety of features, but we will focus on the concentrated collection at the Fountain Paint Pots Nature Trail. This area provides a perfect lesson in the diversity of geothermal activity, as it contains all four major types of features in one small, easily walkable loop. We begin by walking past Silex Spring, a large pool of placid, superheated blue water. It is a classic hot spring, its calmness a result of an open plumbing system that allows heat to be released continuously through the process of convection. Hot, less dense water rises, cools at the surface, and sinks, preventing any buildup of pressure. A short distance away, we hear the constant roar of Clepsydra Geyser. This geyser erupts almost continuously, with water splashing 20 or 30 feet into the air. Its name means water clock in Greek, but ironically, its constant action makes it a poor timekeeper. Its behavior tells us that it has a very rapid recharge and heating cycle, a system that is in a constant state of high energy. But the main attraction here is the feature that gives the area its name. We arrive at a railing overlooking a large, bubbling expanse of mud. These are the fountain paint pots. Here, we must apply our knowledge. From Part 6, we are looking at a geothermal area with abundant heat, but a very limited supply of water. The mud is not being boiled from below. Instead, geothermal gases, including hydrogen sulfide, are rising from the deep heat source and bubbling up through a shallow basin filled with clay and surface water. Microbes in the mud convert the hydrogen sulfide into sulfuric acid. This acid then attacks the surrounding volcanic rock, dissolving it and turning it into fine clay. What we are witnessing is the slow, gurgling digestion of the landscape. The mud is the color of the rock it is made from, a milky gray stained with pinks and browns from iron oxides. We watch as thick bubbles of gas slowly rise to the surface, swell into shiny domes of mud, and then burst with a satisfying plop, splattering the thick slurry. The consistency changes with the seasons. In the wet spring, it is a thin, soupy broth. In the dry late summer, it becomes a thick, cement-like paste, and the plopping bubbles are much more dramatic. The fountain paint pots are a perfect example of this strange and fascinating type of feature, a world of acid, microbes, and dissolving rock. For our final stop, we travel to the northernmost of the major basins, the Norris Geyser Basin. Norris is different from all the others. The moment you step onto the boardwalk, you can feel it. The air is hotter, the steam is thicker, and the smell of sulfur is more pungent. The landscape is more stark, more barren and alien. Norris is the hottest, most acidic, and most changeable of all of Yellowstone's geyser basins. This is because it sits at the intersection of three major geological faults. These deep cracks in the Earth's crust provide very direct pathways for heat and gas to escape from the magma chamber, making the entire area incredibly dynamic. Features at Norris can appear and disappear overnight. Water temperatures can fluctuate wildly, and the ground is constantly being altered by the intense heat and acidic vapors. The basin is divided into two parts. First, we walk through the Porcelain Basin. It is a vast, open expanse of almost white ground. almost completely devoid of trees. The ground is pale sinter, and from hundreds of small vents, hissing fumaroles release clouds of steam. Small, vividly colored springs of turquoise and yellow are dotted across the landscape. The sheer number of steaming, hissing sources of heat is overwhelming. It feels like walking across the thin lid of a boiling pot. We then proceed to the back basin, which has a very different character, with features scattered among a lodgepole pine forest. Here we find a geyser, one of the few large geysers in Yellowstone, whose water is acidic rather than alkaline. And here we also find the undisputed king of all geysers. We arrive at the vent of Steamboat Geyser. Most of the time, Steamboat is not very impressive to look at. It splashes water 15 to 40 feet high in frequent minor eruptions, and a powerful steam vent next to it roars constantly. But Steamboat holds the title of the world's tallest active geyser. Its major eruptions are rare and completely unpredictable. It can go decades between major eruptions, or it can have several in a single year. Its plumbing system is thought to be immensely deep, vast, and complex, so its recharge and heating cycle is not stable like Old Faithful's. But when it does have a major eruption, it is an event of unimaginable power. The eruption begins with a column of water that rockets over 300 feet into the air, sometimes as high as 400 feet. That is taller than the Statue of Liberty. The roar is deafening and can be heard for miles. The water phase lasts for 10 to 40 minutes, followed by a steam phase that can last for more than a day, releasing a colossal and continuous jet of steam with the force and sound of a locomotive. To witness a major eruption of Steamboat Geyser is to witness the raw, untamed power of the Yellowstone volcano in its most dramatic form. It is a fittingly powerful and unpredictable feature for this wildest of geyser basins. Our walking tour is now complete. We have traveled from the predictable grandeur of the upper geyser basin to the otherworldly colors of Midway, the geological diversity of the lower basin, and finally to the raw, chaotic power of Norris. At each stop, we have seen how the same basic ingredients, deep heat, percolating water, and a specific type of plumbing, can combine in subtly different ways to create an almost infinite variety of natural wonders. Every hissing vent, every bubbling mud pot, every serene blue pool, and every thundering geyser is just a different dialect of the same geological language. They are all surface expressions of the one great truth of this land, that we are walking on the roof of a vast and active volcano. Part 8. The Terraces of Mammoth and a Changing World. We have now spent a great deal of time exploring the major geyser basins of Yellowstone. We have walked the boardwalks, felt the steam on our faces, and understood the mechanics of geysers and the biology of colorful hot springs. In all the places we have visited so far, Upper, Midway, Lower, and Norris geyser basins, there has been a common geological thread. They are all located within the boundaries of the ancient Yellowstone caldera, the giant crater left by the last super eruption. And, crucially, the rock beneath them is all the same. It is volcanic rhyolite, a rock that is rich in the mineral silica. This silica is what creates the geyser cones, seals the plumbing systems to allow pressure to build, and forms the broad, hard center sheets around the hot springs. However, Yellowstone is a vast place, and not all of its wonders are built from the same material. For the final part of our lecture, we will travel to the northernmost edge of the park. to an area that lies outside the caldera boundary, an area that is geologically distinct from everything we have seen so far. We will visit the Mammoth Hot Springs. Here we will find no geysers, and we will find no silica. Instead, we will find a surreal landscape of massive, tiered terraces, built not from hard, glassy sinter, but from a softer, chalky mineral called travertine. We will explore the chemistry that creates these structures, and then we will conclude our entire lecture with a final reflection on the dynamic, ever-changing nature of this remarkable place. To understand Mammoth Hot Springs, we must first understand the rock that lies beneath it. Unlike the interior of the park, which is dominated by volcanic rock, the foundation of the Mammoth area is a thick layer of sedimentary rock called limestone. This limestone was formed hundreds of millions of years ago, long before the Yellowstone volcano existed. It was formed at the bottom of a shallow, ancient sea that once covered this part of North America. The limestone is made up of the compressed shells and skeletons of countless marine organisms, which are composed primarily of a mineral called calcium carbonate. This difference in the underlying rock changes everything about the geothermal features on the surface. It changes the chemistry of the water, the nature of the deposits, and the appearance of the landscape. The story of Mammoth begins, like all stories in Yellowstone, with heat and water. The heat source here is thought to be related to the same vast magma system, but it is likely a peripheral part of it. Hot water from deep underground rises towards the surface. As this hot water travels upwards, it passes through the thick layers of ancient limestone. But this water is not pure. It contains a significant amount of dissolved carbon dioxide gas, which it has picked up from magmatic sources deep within the earth. When carbon dioxide gas is dissolved in water, it forms a weak acid called carbonic acid. This is the same acid that is found in soda water. So, what we have is a vast flow of hot, acidic water moving through a layer of limestone. Limestone is a rock that is very easily dissolved by acid. As the hot, carbonic, acid-rich water flows through the cracks and fissures in the limestone, a chemical reaction occurs. The acid dissolves the calcium carbonate from the rock. The water becomes heavily laden, fully saturated with this dissolved calcium carbonate. It is carrying a massive load of dissolved mineral. This mineral-rich water continues its journey to the surface, eventually emerging on the hillside at Mammoth Hot Springs. When this water flows out of the ground and onto the surface, the conditions change instantly. First, the pressure on the water is released. This drop in pressure allows the dissolved carbon dioxide gas to escape from the water and enter the atmosphere, much like the bubbles escaping when you open a bottle of soda. Second, the water begins to cool rapidly as it is exposed to the air. Both of these factors, the loss of carbon dioxide and the drop in temperature, dramatically reduce the water's ability to hold the dissolved calcium carbonate in solution. The water can no longer carry its mineral load. Therefore, the calcium carbonate must come out of the solution and become a solid again. This process is called precipitation. The calcium carbonate precipitates out of the water as a mineral called travertine. Travertine is a form of limestone. It is a relatively soft, chalky, and porous rock. At Mammoth, this deposition happens at an incredibly fast rate, while the siliceous sinter in the geyser basins might accumulate at a rate of less than an inch per century. The travertine at Mammoth can accumulate at a rate of up to several feet per year. This rapid deposition is what allows the majestic and fast-changing structures of Mammoth to form. As the hot water flows out of a vent on the hillside, it spreads out. As it cools and loses gas, it deposits a rim of travertine. The water then flows over this rim and down the slope, depositing more travertine as it goes. Over time, this creates a series of small pools, each one dammed by a rim of newly formed rock. As the water flows from one pool to the next, it builds the rims higher and higher and extends them outwards. The result is a breathtaking cascade of terraced pools, looking like a giant frozen waterfall made of white stone, or an enormous, intricate wedding cake. These are the famous travertine terraces of Mammoth. The appearance of these terraces is stunning. When they are active, with hot water flowing over them, the travertine is a brilliant, blinding white. However, just like in the other hot springs, life finds a way to inhabit this environment. Thermophilic bacteria and algae colonize the warm water in the pools and on the wet faces of the terraces. These microorganisms add their own colors to the white canvas of the rock. You will see streaks and bands of rich brown, rusty orange, and deep green, painting the front of the terraces and lining the bottoms of the pools. These colors, combined with the stark white of the fresh travertine and the steam rising from the hot water, create a landscape of exceptional beauty. The terraces can grow to be enormous. Some are hundreds of feet high and cover acres of ground. But the most defining characteristic of Mammoth Hot Springs is change. Because travertine is deposited so quickly, the features here can change their appearance dramatically in a very short amount of time. A vent that is active today, pouring water over a beautiful, colorful terrace, might become clogged with its own mineral deposits within a few months or years. When the water flow stops, the terrace dies. The colorful thermophiles dry up and disappear. The brilliant white travertine, now exposed to the elements without the constant bath of hot water, begins to weather. It turns a dull, crumbling gray. The terrace becomes a dry, ghostly skeleton of its former self. Meanwhile, the hot water, having been blocked from its original vent, will find a new crack in the ground nearby. It will burst forth in a new location, sometimes right in the middle of a walking path or in a clump of trees. The process begins anew. The water flows, the travertine precipitates, and a brand new terrace begins to grow, engulfing the trees and changing the landscape. Dead trees, their trunks bleached white and their bases buried in rock, are a common sight at Mammoth, silent witnesses to the restless nature of the springs. A visitor returning to Mammoth after an absence of 5 or 10 years might find the landscape completely altered. A once glorious terrace might be dry and gray, while a new vibrant one has grown up in a place that was previously just a patch of forest. This constant cycle of birth, growth, death, and rebirth makes Mammoth Hot Springs one of the most dynamic and rapidly changing geological features on the planet. A walk along the boardwalks of the Mammoth Terraces is a walk through this history of constant change. The lower terraces are a maze of active and inactive features. You can see the famous Liberty Cap, a 37-foot tall cone of extinct hot spring travertine. It stands alone, dry and gray, a monument to a spring that ceased to flow long ago. Nearby, you might see the Pallet Spring, where water flows over a crisscrossing network of ridges, creating a beautiful pattern of brown, orange, and white. An upper loop drive takes you to the upper terraces, where you can see vast, flat expanses of new travertine, large active springs like Canary Spring with its vibrant yellow-orange bacteria, and extensive fields of old, gray, decaying terraces that are slowly being reclaimed by the forest. It is a stark and beautiful demonstration of geology in action, a place where you can literally watch the landscape being built and destroyed before your eyes. The difference between Mammoth and the geyser basins brings us to an important realization. The geothermal features of Yellowstone are not all the same. They are shaped by the specific local conditions of the geology. The presence of limestone here, instead of rhyolite, completely alters the chemistry and the resulting formations. There are no geysers here because the travertine rock is too soft and porous to form the strong, pressure-tight plumbing systems that are required for an eruption. If pressure tried to build up, the soft rock would simply crack and leak, or the vent would be blown out. So, Mammoth is a land of silent, flowing springs and continuously growing mountains of stone. Now, as we reach the end of our long lecture, let us take a step back. We have looked at the parts in great detail. We have examined the heat, the water, the plumbing, the life, the chemistry, and the specific locations. Now, let us look at the whole. Let us think about Yellowstone not just as a collection of interesting features, but as a single, living, breathing geological entity. The most important takeaway from all that we have discussed is that Yellowstone is not a museum. It is not a static collection of rocks and water features that have been preserved in time. It is an active, dynamic, and constantly changing system. It is alive in a geological sense. The ground beneath the park is constantly moving. It rises and falls as the great magma chamber below inflates with new molten rock and deflates as gases and heat escape. These movements are measured in centimeters per year, a pace that is imperceptible to us, but rapid in geological time. Earthquakes are a daily occurrence in the park. Most are too small to be felt by humans, detected only by sensitive seismographs, but they are a constant reminder of the immense stresses in the crust. Swarms of thousands of small earthquakes can occur over a period of weeks or months as fluids and magma move around deep underground. These earthquakes are the primary agents of change for the hydrothermal features. A small shake can open a new crack in the rock, creating a new hot spring. It can close an existing crack, shutting off the water supply to a geyser and causing it to become dormant. It can alter the shape of a geyser's plumbing, changing its eruption interval from predictable to erratic, or vice versa. The landscape of Yellowstone is in a constant state of flux. Hot springs can heat up and become geysers. Geysers can lose their energy and become quiet pools. Mud pots can dry up into steam vents, or steam vents can be flooded to become boiling springs. The colors of the pools change as the temperatures shift. The terraces at Mammoth grow, die, and shift location. Nothing in Yellowstone is permanent. What you see today is just a snapshot in time, a momentary configuration of a system that has been evolving for millions of years and will continue to evolve long after we are gone. Scientists from the United States Geological Survey and the National Park Service constantly monitor the park. They measure the temperature and chemistry of the water. They track the eruption intervals of the geysers. They use GPS and satellite data to measure the swelling and sinking of the ground. They deploy networks of seismometers to listen to the earthquakes. This monitoring is not just for scientific curiosity. It is to understand the behavior of the massive volcano that lies beneath. While a super eruption is not thought to be imminent, the system is still very much active. Understanding its normal cycles of breathing, shaking, and heating is crucial. For us, as observers, this dynamic nature adds a layer of profound wonder to the experience. When we watch Old Faithful erupt, we are not watching a mechanical clock. We are watching the Earth release a breath of accumulated energy. When we look into the depths of the Grand Prismatic Spring, we are looking into a direct conduit to a world of subterranean fire. When we walk across a geyser basin, we are walking on a thin crust over a vast, hot, and pressurized reservoir. We are small, transient visitors in a land governed by forces of immense power and ancient timescales. So, tonight, as you let your mind rest, let it drift to this incredible place. Picture the snow falling silently on the vast pine forests of the plateau, adding to the deep snowpack that will fuel the geysers next year. Picture the water, miles deep in the dark, hot rock, slowly seeping through microscopic cracks, gathering heat and minerals. Picture the silent, steady growth of the travertine terraces under the starlight. Picture the heat engine, the great plume of the Earth's mantle, burning steadily, a timeless fire that shapes the world above. Yellowstone is a place where the veil between the surface world and the deep earth is thin. It is a place where we can witness the fundamental processes of our planet in their most raw and beautiful forms. It is a story of heat, water, rock, time, and life, all woven together into a tapestry of endless wonder. It is a story that has no end, a cycle that continues, indifferent to our presence, calm, powerful, and eternal. Thank you for listening to this lecture on the geysers and hot springs of Yellowstone. I hope it has been informative, and more importantly, I hope it has provided a calm and steady background for your rest. You may now let go of the images and the information. There is no test. There is nothing more to learn tonight. Just let the quiet rhythm of the Earth's slow processes guide you into sleep. Good night.